everyone, today we are finally going to be implementing the entirety of the Wav2Vec2 architecture. We're going to write the model, we're going to write a training script or pre-training script, we're going to write a fine-tuning script for the speech recognition task. We're going to do the entire thing. Now, this is going to be a fairly advanced implementation, so if you are not already comfortable with things like transformers, working with neural networks, working with audio, or if you've never trained a speech recognizer before, like the Deep Speech 2 architecture, then I would highly recommend just going back and watching a couple of those videos first. They're already in my channel, and I will link them down below. Get comfortable with working audio, and then come back here, and this will make a lot more sense. So to implement the architecture, there's a couple of things that we're going to need to do. The hardest part actually will be our utility functions, and that's essentially going to be the entire contrastive task. And so I have a video covering the general ideas behind the Wav2Vec architecture. We did essentially a paper overview, so you can go ahead and watch that first if you want some more specific details. But the main idea behind our Wav2Vec architecture is this. We're going to train it on raw waveforms, hence it's called Wav2Vec. We're going to pass it through some convolutions, and then the output of this convolution, we're going to quantize them with the Gumbel-Softmax Quantizer. And then we're going to mask the outputs of the convolution, pass it to the transformer, and then our transformer's goal is to minimize the cosine similarity between its output embedding and our corresponding quantized vector, right? So we want to minimize the distance between this one and this one because these two go together. And I want to maximize the distance between this and everything else. So we're going to reference back to the paper as we're going, but let's just go ahead and start working on some of the fundamental things that we're going to need. So to do this, I've already added a little bit of code here. There's nothing fancy in here. We'll look at this one later. This is just to organize our output, but I put in an entire config file here, which defines the structure of the model. For now, the only things we're going to care about is this stuff right here, the size of the convolutions. So in the Wav2Vec architecture, there is a CNN, a convolutional encoder, and here's the definition of that. So we're going to say that each convolution will have a embedding dim of 512. The first convolution has a kernel size of, and let's make this all a little bit easier to see, make it a little bit bigger. There we go, close that. We'll have a kernel size of 5. Or a stride of 5, and then we're going to do strides of 2 for all the other subsequent convolutions. And then the kernel size will be 10 for the first convolution, it'll be 3 for all of these, and then 2 for these last couple ones. So this is what we're going to focus on right now to write our convolutional encoder. So one thing we need to keep in mind is the fact that audio is not all of the same length. And so what do I mean by that? In audio, we typically have, let's say we'll have one waveform. It'll look like this, right? We have some audio, and then we'll have another audio file, and it'll look kind of like this, but it won't necessarily be the same length, because of course every audio file will be of different lengths. And so we have to somehow work on this. And the way we do this is typically padding, right? We're going to have padding. We're going to take our shorter audio file and just add some padding values to it so they're the same length, right? Standard setup. This means that when I apply convolutions to it, I'm going to get some embeddings, right? I'm going to get some representations. So I'll have these representations right here. And then, of course, for the other one, I'll get some other representations, right? For the second sample. But because my second sample is not as long as the first one, some of these embeddings will have come from the padding region, right? So when I convolve my signal, my convolution is going to go from left to right, which means some of the convolution is going to be coming from this padded area. And so what I want to know is, what is the output size versus the input size? Or essentially, which of my output embeddings from the convolution correspond to the different padding regions? And the reason we need to do this is because after all of this is going to go to some transformer, right? Transformer. And we want to make sure the transformer is not attending to the padding regions or the padding embeddings, right? Because again, this is not a part of the original data, so we'll have an attention mask for these padding regions. So let's go ahead and write that very first method, which is going to compute, it's going to compute the encoded lengths. And so to do this, let's go ahead and just create some fake data first. We're going to do sequence lengths. Let's say our first audio is of length 25,000 samples in the first audio, and then the second one, let's say there's 32,000 samples. And so our data will be torch torch.randn, generate some data, and it'll be of the length L for L in sequence length. And then our attention mask, right? This will be the attention mask on the original audio, right? So this is going to be torch.ones L for L in sequence length, just like that. And so our data is going to be torch.nn.utils.rnn.pad sequence. And it's going to be the data. We're going to pad our audio, so padding value will be 0. We'll pad them with 0, and we'll make it batch first equals true because that's how we typically work on this stuff. Similarly, our attention mask is going to be torch.nn.utils.rnn.pad sequence. Again, attention mask, padding value equals 0, and again, batch first equals true. So let's go ahead and look at this. So if we do print data, and we can also print the attention mask, print attention mask, you will see that Python utils, right? There we go. So we can see that here's my second audio. My second audio is longer, as we can see, it's 32,000. So we have 32,000 numbers here that will represent that audio. My first audio is shorter. It only has 25,000 things in it. So it's going to be the first 25,000 things and then padded with zeros to the end. And then its corresponding attention mask is going to be, here are, in my second sample, all of these values are legit audio, right? It's not some padding value. So it's going to be 1 for everything. And then we have 1 for the first 25,000 samples here, that is actual audio data, and then zeros for the rest of the padded regions. And that's essentially referencing back to this. We have 1s for everything that's actual audio, and then zeros for everything that isn't actual audio, right? We're going to have these padding masks. Now again, the attention mask at this audio level isn't what's interesting to us, because we're going to be doing a convolution. What we want is the attention mask at the convolved dimensions, right? Once we perform the convolution. So that's what we're going to be computing now. What is the length of my sequence after I apply some convolutions to it? That's what I want to compute. So if this had 25,000 things, and I apply some convolutions to it where I already know the definitions of the convolutions. I know its stride, its kernel size, all that sort of stuff. If I know that, then what will that output sequence look like? And this is relatively straightforward to do because PyTorch gives us the formula ahead of time. So in PyTorch, let's pull up the conv1d docs. They give us this already. We know that if we apply a convolution with this padding and this kernel size and this stride, then the output shape has this formula, right? If I know what the input shape is, then I know exactly what the length of the output shape is. It's just I have multiple convolutions, so I'll be repeating this operation over and over again on my dimensions. So this is exactly what we're going to be computing. So to start with this, let's go ahead and do def compute encoded lengths. And this is going to take in the lengths. So this is the duration, or the number of samples in every single audio file. We have our con kernels, and then we have our con strides, right? So this is going to be the kernel size of every single convolution, and this is going to be the stride of every single convolution. And to do all this, we're again going to need our config. It'll be the Wav2Vec2 config. We'll use the defaults, but we can see we have our con stride and kernel size already set in our config. So that's what we'll be using. And so the first step will be we want to compute the, compute encoded lengths. We're going to pass in the sequence length. We're going to pass in config dot our, the first thing I wanted was kernel size, so con kernel, and then config dot con stride. That's what we're going to pass in. And so in here, we're going to get print lengths, con kernels, con strides. And this should give us what we're looking for. Yep, so this is the length of my audios, this is my kernel sizes, and this is the strides I'll be using. So let's just go ahead and do it. Of course, if, just as a sanity check, which was helpful here, if is instance, if the lengths here is just currently a list, we don't want it to be a list, we want it to be a tensor, so we can just do easy operations on it. So if not is instance, if the lengths is not torch.tensor, then just go ahead and do lengths is equal to torch.tensor go ahead and convert it to a tensor. So now we can do our operation. So now we know the formula. We know compute conv out. If I have some lengths, and I know the kernel size, and I know the stride, right, stride. If I know these things, then I know the formula. We have to do the formula as per the PyTorch documentations. It was a torch.floor function. We're going to do lengths minus kernel size minus 1 divided by stride plus 1. And again, this comes directly from the formulation provided by the PyTorch documentations, right? There was basically we take our lengths, subtract from the kernel. There's no padding or anything, so it's kind of simplified. So we have our kernel size. We're going to subtract 1 from it, subtract 1 from it again. Here, divide by stride, add 1, just copying the formula from PyTorch. And so now that we have that, we can do for kernel size stride in zip con kernels con strides, right? So we're going to loop through every pair of kernel and stride for all the different convolutions we plan on doing. And we're going to do lengths is equal to compute conv out lengths. And we're just going to repeat this operation over and over again with this k and this s. And so if we print out our lengths at the end, we'll see that we get something like this. And let's actually print it out at the beginning as well. Let's do this here. All right, so we're going to start with a 25,000 sample signal and a 32,000 sample signal. After the first convolution becomes about 4999 and then 6399. After the second convolution becomes 2499, 3199. And we just repeat this over and over again until we've convolved all the way down through all the convolutions. So our final signal, the 25,000 samples, will produce 77 valid embeddings. My 32,000 samples will produce 99 valid embeddings. Valid time steps, which means my 77 will need to be padded to the 99 before I give it to the transformer, right? So this is essentially what we've computed here is this thing has 77 length and this thing has 99 length. And so we're going to have to pad 22 pad tokens essentially here to fill in the matrix before we pass it to the transformer. And so that's basically it, right? This is us computing our encoded lengths, and we can return length. And we did something very similar in our DeepSpeech 2 implementation because we needed exactly this information, which outputs of the convolution are valid and which outputs of the convolution are not valid because the different audios are of different lengths. Just as a helpful thing, we can do lengths.type torch.int, right? These are just values, integer values, so we can just make them integer values just like that. And so now that we have that, we can go ahead and compute our sub-attention mask. So def compute sub-attention mask. So the sub-attention mask, the attention mask that we've created up till now, is at the signal level, right? It's done on the raw audio. But I want the attention mask on the encoded level. So I know which tokens are pad tokens and which tokens are not pad tokens in our compressed representation over here. And so this is all I'm going to be doing. I'm going to be computing the sub-attention mask, and of course we're going to be using this method up here to do that. And so this is again going to take some config. It's going to take some attention mask. This is going to be the original attention mask. And what we can do is first our batch size, right? Batch size is going to be just equal to the attention mask dot shape 0. Just grab that first dimension. And then our raw length is going to be attention mask dot sum axis is -1. Because again, remember, our attention mask is 1 for all the valid values in our data and 0 for the invalid ones. So if I just add up all the ones, that tells me how many samples of data I have in my actual data. That's valid. So leng lengths. There we go. So that's my raw lengths of my actual data. And so my encoded lengths is going to be our compute encoded lengths, the method we just wrote above. We're going to pass in our raw lengths. We're going to give it the config.conKernel and config.conStride. Oh, conStride. Just like we had, right? Just like we did down here, nothing new. So we can actually delete U and do compute sub-attention mask. And let's call this our, I believe I just called it the sub-attention mask. So let's just put that here, sub-attention mask. It's going to be that. And we will then be doing our, we're just going to pass in our config and our attention mask, right? Config and attention mask. Good. So now that we have that, we have our encoded lengths. So let's go ahead and create. So again, print encoded lengths. We should get the same values because nothing changed. And let's get rid of this print right here. Just keep it clean. There we go. We have 77, 99. So my attention mask, my sub-attention mask, is going to be the first 77 things in my first sample is valid, and all 99 things in my second sample is valid, which means the extra 22 pad tokens I need to add to this to get to there is not valid. So that's what we're going to be doing right here. So we're going to do our sub-attention mask is going to equal to, it's going to be just torch.zeros. Right, torch.zeros, and it's going to be in the shape of batch size by max encoded length. So whatever the longest thing is. And then we can just loop through our data for index length in enumerate encoded lengths. Right, just loop through everything. Our sub-attention mask for that index, everything up to that length will be 1. Right, so that's me indicating in the first sample, the first 77 things are valid. In the second sample, all 99 things will be valid. And there we go. So we have our sub-attention mask right here. And I should spell that correctly. And once we have that, we can return our sub-attention mask. So we can now take a look, print sub-attention mask. And we can see the output of this specific convolution will say that if our first sample at 25,000 things and the second sample at 32,000 things, the first 77 things are valid because the first signal is shorter, and then everything after that is pad. And then the second one is the longest thing, so everything will be valid. And this is just some housekeeping that we essentially have to do to make sure we are attending to the right things and not attending to the right things in the transformer after the convolution. So we just need to process our attention mask as if the convolutions are already done. So we can just pre-compute that stuff, and that's exactly what this is. Great. Now that we have that, let's start the first part of our actual architecture detail, and that's the span mask. So def compute span mask. So let's remind ourselves what span masking was. Let's just search for it, span. There we go. Span mask, here we go. So models are implemented in FairStack. For masking, we sample 0.065 of all time steps to be starting indices and mask the subsequent 10 time steps. This results in approximately 49% of all time steps being masked with a mean span length of 14.7. Okay, so what is span masking? So we talked about this in our paper review, but the main idea was that our goal is to essentially do something that's kind of like mass language modeling. It's just in standard BERT architectures or Roberta, you randomly delete 15% of the tokens or whatever from your sequence. And that's kind of fine for the purposes of text, but in audio, subsequent or consecutive embeddings typically have a high amount of correlation with each other. Like this embedding here will be not too different from the one before and the one after, because there's just so much correlation between them, because audio always has correlation and the convolutions have some overlapping receptive field. And so instead of just randomly deleting some percentage of embeddings, why not delete spans of them? We're going to mask out spans of them. And so the way they do it is they randomly sample 0.065 of the embeddings to be selected to span or to mask, and then we're going to mask that one and the next 10. Right, so that's basically it. We're going to do span masking. So let's go ahead and define that. So we're going to compute our span mask. To do this, we need to give it a couple things. First, the shape of the data that we're going to be working on. We need our mask prob. We see that they set that to 0.065. We have our mask length. This is going to be 10, right? We're going to mask 10 subsequent steps. And then min masks is 2. And this is just for sanity check, and you'll see where that is. And lastly, we have our attention mask, and this is going to be none by default, but we're going to need that as well, because of course we don't want to mask out pad tokens. That doesn't make any sense. So we're going to have to just deal with that extra condition right here. And so to do all this, we're going to first do we're going to compute our span mask on our, let's see here, the shape will equal to a tuple. We're going to pass them in as tuples of the sub attention mask dot shape, right? Because the span masking happens on the encoded dimension, right? So afterwards. So in our case, we'll have 77 things in one of them, 99 in the other one, and the span masking is going to happen on that. So we're just going to pass it the shape right here. So we have the shape, and then we'll pass in the attention mask is the sub attention mask. There we go. And everything else we can just leave as defaults. So if we print out the shape again, just to be clear, right, we're going to get this. It's 2 by 99 things. That's the shape of our data that we have here. But of course, only the first 77 things are valid on that very first sample. Okay, so how we're going to do this, it's relatively straightforward. We're going to do batch size by sequence len is going to, and let's call it the total sequence len is going to gth, doing that, is going to be shape, right? That's our shape. Those are the two dimensions we pass in, and we can do if attention mask is not none as a sanity check, then our sequence lengths is going to be our, and let's do this for is none. So if it is none, it's going to be the total sequence length times the batch size, right? So else, right? Else sequence length, it's going to be the attention mask dot sum axis equals -1, and we can convert it to a integer and then a list. So all we've done here is we got the output sequence length. If we don't pass in an attention mask, then everything is valid, and that means if we pass in 99 things, that means the first thing is 99 things in it, the second thing is 99 things in it, ... So however many things you have in your batch. If we do pass in an attention mask, which we will be during training time for sure, then we're going to just add them up, and only the first 77 things are valid in the first thing, and then only the first 99 things are valid in the second thing. So I'm just computing the sequence lengths of the encoded output. That's it. And we just store those values in a list, and we'll get print sequence lengths. We'll get essentially this. That's 77 and 99. We get it back again. And so now let's go ahead and do our sequence masks. Sequence masks, empty list. We're going to do for length in sequence lengths, right? So for every single one of these, gth, make sure I didn't do that, length. Our mask, so we're going to do this sample by sample just to keep it easy. It's going to be torch.zeros, total sequence length. Because of course our mask has to cover the entire max sequence length, like whatever the longest thing is. But in the first case, only the first 77 are valid, and we'll handle that. And we'll set this to a Boolean, right? Boolean. So if we print out the mask and throw a break in there, you'll see that this is just going to set everything to false. So these are my false values. Now that we have that, we've computed a mask. Let's do our sample starting index, right? We're going to go ahead and sample starting indexes, and it's going to be torch.rand length less than the mask prob. So we're going to generate random numbers between 0 and 1, and then check which one of those are less than our masking probability, which in this case is set to 0.065, and we can do print sample starting index. And we'll get some, let's see here, not mask length, sorry, mask prob, my bad. So we'll get some trues where it's true, and then falses for everywhere else, which means if this value is true, I want my span mask to start here and go 10 indexes forward, span everything after that. And so that's what we're going to have to do now. The easiest way to do this is, instead of just having a Boolean list of trues and false, it'd be easier to know where the trues and falses are, like the index of them. So let's find the indexes of the trues. And PyTorch has a nice little function that lets you do this called non-zero. And non-zero will give you the indexes of trues. So in this case, it's a little bit easier if we do print. Let's do this. Print sample starting index, and then the same thing, dot non-zero. And it should be clear. So we can see the first thing here, the 0th index is true, so 0. And then we have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So the 15th thing is true, so you have 15. So this is just an index, along our list of where things are false, essentially, or where they're true. So we have to put the non-zero right here. And what we're going to do is if len sample starting index is less than min mask, and this is our sanity check. We always want to make sure we have something masked no matter what. So if for some reason in this random selection nothing at all was masked, we're going to make sure that at least 2 things are masked, and we'll just kind of fix it ourselves. So we'll do sampled starting index is going to be torch.rand int low equals 0, high equals length. Just pick, just sample some value between 0 and the length of this thing. And we'll do size equals min masks 1. So just go ahead and randomly sample 2 values here, 2 values, to be the starting points. So basically, if when we selected the random starting points, if for some reason, by chance, nothing was selected, go ahead and select just 2 random numbers from our indexes here to do it. So we, instead of having all of these, we just have 2 things. But that's just a sanity check in case, in case nothing is selected. Okay, good. So now that we have all that, sanity check, we can do our span. Offsets is going to be torch.arange mask length. So if we look at our print our span offsets out, it'll be exactly what you think. It's just a list from 0 to 9 because we have 10 things that we want. And all we need to do now is just an easy spans is going to be equal to sampled starting index plus the span offsets. So we're just adding to one list the other, one thing to the other thing, and we can look at our spans now. It'll look like this, and the easiest way maybe is let's also print out our sample starting index. And so we can see from 8, we're going to span mask from 8 to 17. From 9, we're going to span mask from 9 to 18. From 24, we're going to span mask from 24 to 33. And you can see there's going to be some overlap, right? So there's heavy overlap between these spans, but that's okay. That's no problem. In the end, we effectively end up, masking about 50% or so of the data after we kind of collect it all together. So that is our span mask, indexes of what samples we want to mask out. So those are our spans. And so now we can do spans is equal to spans.flatten, right? So if we do spans, this is just going to be a flattened list with some potentially overlapping and repeating numbers, but that's okay, right? So we have that. Now, one thing we want to make sure is that when we're selecting something to mask, right, we don't want to mask padding tokens, right? If I know that only the first 77 things are valid and all 22 things after that are invalid, we want to make sure we're not selecting pad tokens to be masked because that doesn't make any sense. So what we'll do is we'll do a sanity check. Our spans is going to be spans, where our spans is less than or equal to the length minus 1, length minus 1. So this is just going to go ahead and index out or remove any one of these things that are longer than the valid length. And so that's what we have left. Yeah, so there we go. So we can see everything up to 76 is fair game. Anything after 76, so 77 and forward, is not fair game because those would have been pad tokens, right? So we don't want to end up masking out pad tokens. And so now we have our valid set of spans. And so lastly, we can do our mask spans dot flatten, right? Go ahead and just flatten it again, is true. So basically in our mask, we want to set these values to true. And so finally, if we look at our mask, we're just going to essentially set those indexes to true. So these indexes were selected to be masked, so that's the span that was selected. These indexes were selected to be masked, that's the span that we're indexing and setting to true. And so these are the indexes that have been essentially saying these are the ones we want to mask for our contrastive pre-training. And so then we can do our sequence lengths, or sequence masks.append mask. Just go ahead and store them. Of course, we're going to repeat this for every single sample. So then we can do a sequence mask is going to be equal to torch.concatenate sequence mask. Masks, just go ahead and print it out. See our final one. And we can see in the first sample, these were selected to be masked. In the second sample, we have stuff at the end that's selected to be masked, but that's okay, because all of these are valid, right? Everything in the second sample is valid because it was longer. But in the first sample, that's not the case, right? We don't want to do that. And so that's everything we need to do our span masking, right? Nothing too crazy. Okay. And actually, one thing, if you notice something that went wrong, this just concatenated everything together as a list. We need that batch dimension there. So we need to add a batch dimension here, unsqueeze 0. And now we'll get that. So we have our first sample, and then we can see we have the second sample here. So just to get the shapes correct. So dot shape, it should be exactly 2 by 99. And we have our indicator of what things are selected to be masked, what things are not. And so we can return sequence masks. And there we go, right? So now we have our logic to identify what tokens were selected to be masked and what tokens are not selected to be masked. Nothing crazy. Now for the toughest part of what I think in this entire implementation, maybe not toughest, but just annoying. We can do our span mask is that. So these are the ones that we've selected to mask. When we've selected something to mask, we now need to set up our negative. So let's go ahead and look at the negatives here. Let's see, where in the paper was it? Other masked timestamps. Here we go. So for the contrastive loss, given a context network output CT, we need k+1 quantized candidate representations, which includes QT, which is the correct answer, and k distractors. Distractors are uniformly sampled from other masked time steps. So this is actually in my paper overview. I've pinned a comment to that video because I actually got this slightly incorrect when I described it. But the key idea is distractors are uniformly sampled from other masked time steps. So let's just go ahead and understand exactly what that means. Let's just do it for a batch size of 1, right? Just to keep it simple. So we're gonna have some embeddings. So let's say we have, I'm just going to draw a bunch of these out, all of these embeddings. Let's say this was the output of our neural network, or output of the convolutions, and we also have some padding stuff at the end, right? Because this may not have been the longest thing in our batch, but let's just say. And now we've done some span masking, and we've identified that these are the candidates for masking, let's say, and let's say these two here. And this is index 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, right? So now I know for all, and these will be my Z's. So let's go back to the figure and just kind of make sure we're referencing as we're going. These will be my Z's, the latent speech representations that I've extracted from my convolution, right? Convolution. For each one of these things, I have a corresponding Q, a quantized vector that the Gumbel-Softmax did. And we haven't implemented any of this yet, but we'll get there when we get there. So we'll have corresponding quantized vectors for each one of these. And of course, we're still going to have some padding stuff at the end because we don't really care about this. And so I know that for each one of these, so if I masked this index right here, I know the correct answer will be this one right here, Q3. So Z3 goes with, right, Q3. The quantized embedding Q3 is my target for Z3 for the masked. But when I do contrastive learning, I need to contrast it against something. I need some distractors, some negatives, right, to compare against. And so what we're going to do is randomly sample from, let's just look at for Q3, for Z3 specifically, we'll randomly sample from these only. So we're going to look at this one, this one, this one, this one, this one. So if we say we want, let's say 2 distractors, right? 2 distractors, I will random sample from only the other quantized or only the other masked positions. So I'll random sample from, I have index 4, 5, 6, 8, and 9 are my indexes of the masked things. I can't sample from 3, right? Because Q3, right? Position 3 is the correct answer, but I can sample from all the remaining masked positions. So 4, 5, 6, 8, and 9. And so from here, I'll randomly sample 2 values. Let's say I pick 4 and 9. So that means Q4 and Q9 will act as my 2 distractors. So my contrastive learning goal will be to minimize the distance between Z3 and Q3 and maximize it between Z3, Q4, and Z3, Q9. And so this is the thing I got wrong when I mentioned in that video. I said you can just randomly sample, but I pinned it down below. We will only random sample from other masked positions. We won't random sample from like these, right? So Q0 through 2 and then Q7, these will not be selected for random negative selections, right? So they will not be selected. Okay, good. So that's just a small detail, but relatively important. Let's go ahead and implement it, because this is the most annoying part of this entire implementation. So let's go ahead and do it. All right, so to do this, we're going to write a method called def, and it's called this sample negative indexes, or indices. Let's just keep it the same. And in here, we're going to pass in a couple pieces of information. First, the feature shape, just like we did before. The num negatives. How many negatives do you want to sample? This is set to 100 by the paper, so we'll set that later. And then mask time indices, right? And this is going to identify which positions are selected to be masked, which positions are not selected to be masked. Because when I sample my negatives, again, they can only come from masked positions. So I want the quantized embeddings from masked positions only to sample for our negatives. Good. So let's go ahead and start this. So we need to do a quick, let's do our, let's call these negatives. It's going to be equal to sample negative indices, and we'll pass in again, feature shape will be a tuple. And it's going to be the sub attention mask dot shape. And then we have our num negatives. Let's just say it's 5 to keep it easy. And mask time indices is going to be the span mask, right? The span mask tells me what I need. So we'll have batch size by sequence length is going to equal to the features shape, right? And then our sequence index is going to be np.arange sequence length. There we go. So this is just going to be an index like this, right? So it's just going to be, and this will be sequence index. So it's just going to be values from 0 to 99 or 98, right? So there you go, just some indexes. And so let's go ahead and start this. We're going to create a sample of negatives, create an empty tensor that we're going to populate. So we'll just fill it with zeros for now, np.zeros, and the shape is going to be equal to, we'll have a batch size by the sequence length by our num negatives. Print sampled negatives. Very simple. It's just going to be a tensor full of zeros. Yeah, these should be, yeah, numpy is fine. We could have done it in torch too, but it's no problem. And we'll make sure the d type of this is equal to np.int32, right? So we have our negatives. So we're going to populate this with our negatives in a bit. And of course we have one set for the first sample, one set for the second sample. Okay, so we're going to do if sanity check, if mask time indices is none, so if we didn't pass anything in, which we won't during pre-training, but that's fine, then our mask time indices is going to be np.ones, and we're going to do batch size by sequence length, and d type equals bool. So this means if we don't pass in mask time indices, then we're going to say everything is maskable, but of course there's nothing to sample in that case, so this is not that interesting, but that's fine. It's just for sanity checks. So for index in range batch size, so we're going to loop through every sample. We're going to do our batch span mask is going to be the mask time indices index. So let's print out the batch span mask and break it right here. So just like we remember from before, this is for the first sample. These tokens have been selected to be masked, right? Everything that's true, and then that's false or stuff that's not selected to be masked. And what I want is its corresponding mask index. So we can do that too. We can do our mask indexes. It's going to be the sequence index, batch span mask. And what this will tell us is, very simply, masked indexes. So we have, and let's go ahead, and this is where it gets a little bit confusing. So let's just, we have actually two different indexes happening concurrently. So we're gonna just visualize both of them so it's clear. The first thing is a bunch of falses and trues. And the length of this thing is 99 because it goes until the length of the longest thing. We just see lots of falses here. And what I want really isn't the trues and falses. I want the indexes of the trues and falses. So like the 10th thing, the 11th thing, the 12th thing. What is the index of them? We could have also done this exactly as how we had done before. It doesn't really matter. Masked indexes is equal to our batch span mask dot non-zero dot flatten. Right? We could also do it this way, where it'll tell me exactly. Did I spell it wrong? Non-zero, not non-zeros. There we go. Could have also done it this way. Gives me the indexes of what things are set to true, what things are set to false, right? But let's just do it this way, just make it a little bit easier. Really more readable. So that's it. So we've grabbed the index at which our sample has been selected to mask. So we're saying along this specific sample, the 19th thing, the 20th thing, the 21st thing, dot, 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 these have been selected to be masked. And this is the first index that we have. The first index is, here are the indexes in the original sequence that we wanted to mask. And we're going to hold on to this because we're going to use it later. Then we're going to have a second index. And so let's go ahead and do this. Our num masked is going to be the batch span mask.sum. This is just going to tell me how many things have been selected to be masked. In this case, 29 things have been selected to be masked. And of course, it's random, so every time I run it, it'll be a little bit different. That's fine. But our feature index is going to be np.expandDims. And you'll see why. np.arange num masked. And we're going to just add in. So this is expand dims, the same as unsqueeze. But if we print our feature index, you'll get this. We have 0, 1, 2, 3, dot, dot, dot. And where does it go through? Let's print out num masked. And also let's print out masked indexes. Let's print out all three of these things so it's very clear. So our masked indexes tell us that the 30th thing in this sequence has been selected to be masked. The 31st thing has been selected to be masked. The 32nd thing has been selected to be masked, dot, dot, dot. And in total, there are 30 things in this sequence that have been selected to be masked, right? 30 time steps in my sequence have been selected to be masked. So I've created a new index here, going from 0 to 29, where 0 refers to this thing, this time step right here, 30. 1 refers to 31. 2 refers to 32. 3 refers to 33. 29 refers to 76. Right, so that's it. I just have an index here. This list, these indexes here, refer to the indexes of this list up here. And these indexes here refer to the actual signal itself. So you can see there's kind of a, we have an index here, and then these indexes index this list here. A little bit complicated, but that's the main idea. We basically we have 30 things here, so we've created a list of values from 0 to 29, identifying the indexes in here, and we can just do the operations here and then just backtrack. This is the main idea. So let's go ahead and start that. So let's get rid of you, get rid of you, get rid of you. So this is our feature index, but what we'll do is our feature index is going to be equal to np.repeat, and you'll see why we do this in a bit. Feature index num negatives axis equals -1. So now our feature index, all we've done is copy. We had 0 through 29 here. We've just copied it over a bunch. So now we have zeros, ones, twos, dot, 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 right? So we, instead of just, and we have it num negative times. So it used to be like 0, 1, 2, 3. Now it's 0 5 times, 1 5 times, 2 5 times. And you'll see why we did this in a second. It's mostly for a sanity check that we're going to need. And so now let's go ahead and sample some rand indexes. So we're going to do sample index, right? These will be our negatives. It's going to be np.random.randint, right? Randint 0 num masked -1. You'll see why we do that in a second. And size is equal to num masked by num negatives, right? So if we print our sample index, you'll see we have sampled. So we're saying for the first sample, we're going to sample these negatives. For the second time step, we're going to sample these negatives. Third time step, we're going to sample these negatives. Now, there's a couple of things that are not valid here, and you'll see what that is. First of all, our first main sanity check is if our sampled index is equal to the true index. So let's kind of talk about this. It's probably easiest just to draw it out. I've sampled some random numbers. So I know that, let's say Q, let's do it with the example we actually have right here. We're doing it with Q3. So I know that Z3 goes with Q3, right? So Z3 goes with Q3. And I want a random sample from all of these things here. Now, what I've done is I've said that these indexes, 3, 4, 5, 6, 8, 9, I've created a new set of indexes up here. So the indexes will be 0, 1, 2, 3, 4, 5. And 0 refers to time 3, 1 refers to time 4, 2 refers to time 5, ... Right? So that's all it is. And all I've done is I know that there's been 6 things selected to be masked, right? Select 6 things. And I know it goes from 0 to 5 in this this indexing here, which refers to that indexing there, because you can see there's 2 indexes going on. So why not just random sample for every single time step some indexes between 0 and 5. So that means for this one, we'll sample some values between 0 and 5. How many of them? Num negatives worth of them. So if num negatives is 2, then we'll just random sample from 0 to 5. And then again, for this one, sample from 0 to 5, ... And we're going to do this for all the time steps in our sequence. Now, of course, we don't need this information for all the time steps in our sequence. We don't need it here. We don't need it here, because these things were never selected to be masked. We need it for these time steps specifically, and we're going to essentially be taking our data now, taking our selected indexes and filter them. But one other caveat that we have, and this is what we're going to be solving right now, let's say for this time step here, we randomly sample. So we sample from 0, 1, 2, 3, 4, 5. Those are my indexes. Let's say because it's random, let's say I randomly sample 0 and 3. Well, wouldn't it be wrong to, and let's pick a different number just so it's clear, 4. Wouldn't it be wrong to select 0? Because if I sample 0, 4, 0, right, 4 time step 0, if I sample that here, well, that 0 refers to 3, which means I want Z3 to map to Q3, which is Z0 in our new indexing maps to Q0, right? So this is the old index, 3 and 3. This is the new index, 0 and 0. I want Z0 to map to Q0. So I can't sample 0 as a negative, because 0 is the right answer, not the wrong answer. And so we don't want to sample 0 as a negative. And so this is where a sanity check happens, and why we produced this earlier. So if we print out our feature index and we print out our sample index, you'll see the following. So we have for the 0th time step, this is the correct answer, right? So 0 is always the correct answer here, and everything else is valid for negatives. For the first time step, 1 is the correct answer. Everything else, so 0 through 12, are negatives. First time step 2 is the correct answer. And we just repeat this over and over again. So what we're curious about is this: print feature index equal sample index. And you should see something like this. Notice here, and let's look at this one right here. This is true, which means let's look up 1, 2, 3 here. So that's this value right here, 21. Well, we are sampling for the 21st time step some negatives. And we sampled 12, 23, 21, 3, and 13. Those are the negatives that we sampled for the 21st time step. The problem is, if my correct answer is 21 and I'm setting 21 as a negative, then that doesn't work out. So we need to change everywhere where it's equal. So like for the 21st time step, 21 cannot be the negative. We have to use other values as the negative, something else. It has to be something that's not 21. And so that's our sanity check. We're going to just check here, and then we can just update it. So we can do sample index, where our sample index equal feature index, we're just going to add 1 to it. So now that 21 plus equals 1. So now this 21 will become 22. And that basically means for the 21st time step, we sampled 12, 23, 22, 3 and 13. So we've sampled negatives that are not 21. And that's the key idea, right? That's the main thing that I wanted to, makes the indexing, I'd recommend just going through this once yourself. It's what makes the indexing a little bit complicated. So this is essentially telling me this, the feature index we created earlier, tells me what's the correct answer at every single time step. So the correct answer is 0 for all of these, 1 for all of these, 2 for all of these, because this is the 0th time step, the first time step, the second time step. So Z0 goes with Q0. Z1 goes with Q1, Z2 goes with Q2, ... Which means over here, we want Z21 to go with Q21, and our negatives should be everything but Q21. So we want to make sure our negatives don't include that index, and that's why we're checking that here. All the correct answers are 21 here. We check here, it looks like 21, there was an overlap. So we're going to add 1 to this to make it 22. So the negatives is not the correct index. That's basically it. So we're just going to add 1 to everything to make sure it's just a different number. That's all. And now that we have that, we can go ahead and set it. So in our sampled negatives, if we print sampled negatives, we have, and let's spell it correctly, we basically have a blank canvas right now of zeros that we need to fill in. And so what we're going to do is in our sampled negatives, at this specific index, right, because we're looping through the batch dimension, we're going to repeat this over and over again, we're going to pass in the batch span mask. So let's go ahead and print this out. So what we're doing is we're grabbing the batch, and then we're grabbing the indexes that were selected to be masked. Because in this thing, we only need to sample negatives for the samples that were masked. For anything that wasn't masked, we don't really bother. We don't really care about them, right? We don't care what they are. So this is going to go ahead and filter it down a little bit, grabbing a subset of the time steps. There's still 0 right now because we haven't filled in with anything yet, but we grab a subset of the time steps that have been selected to be masked. And what we want to do is fill them with our sampled masked thing. So we'll do our masked indexes. And this is where we actually backtrack. So again, let's print out the masked indexes and print out the sample index just to verify. Here are the masked indexes in the original signal. So in the signal, time step 13, 14, 15, or in our image that we did here, time step 3, 4, 5, 6, 8, and 9 were selected to be masked. But this entire operation we did, 24, all these values here, they're on this other index, this 0, 1, 2, 3, 4, 5, right? So they're on this other index. So we need to map back from 0 through 5 to 3, 4, 5, 6, 8, 9, right? The original indexes in the time step. So to do that, we can essentially grab them like this. So where did you go? Here we go. So we have index 24, and that's my 0 to however many things were selected to be masked. So 24 should go back to the 24th thing in this list. This 0 here, these zeros here, should map to 13. This 2 here, these 2s here, should map to 5 because it's 0, 1, 2. This 3 here should map to 0, 1, 2, 3. So it should map to 16. And we can easily do that, right? We can do print our, we're going to do the masked indexes indexed by our sample index, right? So this will just return a tensor of the same shape. But now we're in the original indexes. So if we do print sample index again, there we go. And run it one more time. Here we go. So we can see that our original indexes from 0 to however many things were selected to be masked were 4, 1, 16, 11, and 16. So samples, or time steps, 4, 1, 16, 11, and 16 were selected to be masked, which means we're using the actual indexes, 32, 29, 44, 39, 44, to be masked in the time step. So this is my 0 to whatever dimension. So in my 0 to 5, that's what this is sampling from. So 0 to sequence line, and we can actually print that out as well. Let's print num mask out as well, just so it's clear. So we have 45 things being masked. So this is sampling between 0 and 44 because those are my indexes out of the 45. But this is the actual indexes in my time step of where those 45 time steps are. So we're just backtracking. So again, this is, again, the most confusing part of this entire implementation. We grabbed our time steps to be masked, 3, 4, 5, 6, 8, 9. We create a new index for them, 0 through 5, which refers to 0 to 3, 1 to 4, 2 to 5, 3 to 6, 4 to 8, 5 to 9. We random sampled indexes from up here in this index from the 0 to 5 index. That's what we did. We also made sure that when we random sampled a negative, for the 0th time step, we can't sample the 0th time step as a negative because that doesn't make any sense, because the 0th time step, the correct answer is the 0th time step. So we need to make sure we sample from all the other options. And so we just added one to fix that for all the overlapping things where they ended up being the same. And now we're just converting back from 0 to 3, 1 to 4, 2 to 5, 3 to 6. And that's it. That's all we're doing. And this creates our, for this mask token, these are the ones we selected as our negatives. For this mask token, we selected these 3 negatives. For this mask token, we selected these 3 negatives. And now it's time to just set this inside our sampled negatives. So let's go ahead and do that right there. And we can get rid of you. And let's print out the sampled negatives. And what you'll see is essentially this. For the time steps that were selected to be masked, I now have indexes of negatives to use. For the time steps that were not selected to be masked, they just stay 0 because we don't really care about them. And you can see we have essentially spans of masking happening, right? Spans of masking. Now, the key idea here is this is 0, 1, 2, 3. This is the 3rd time step in the actual signal. What we did is, so in this case, if we have Z3, the correct answer for Z3 will be Q3, the 3rd quantized embedding. But we selected the 5th, the 71st, the 54th, 71st, and 55th quantized embeddings as negatives. Notice how there's a little bit of an overlap. We reuse 71 twice. That's okay. In practice, there's really nothing we can do about it because we may not have enough quantized embeddings to, perfectly sample unique ones for everything. So we might end up just reusing a couple of them, but that kind of works out in the end because our signals will be much longer than 25,000 samples or 32,000 samples, and we're going to be sampling lots of them. So it's okay if there's some overlap in our negatives, but that's the important part. So in the end, it ends up looking something like this. Q3, the correct answer, or let's do it the other way around, Z3, and let's check it right here. Z3, 0, 1, 2, 3. Z3, the correct answer will be 3, right? This is the correct answer. And I selected some negatives. The negatives will be index 5, 71, 54, 71, 55. 5, 71, 54, 71, 55. And so we want to minimize, this will be Q3, right, the index, and then this will be Q5, Q71, Q54, Q71, Q55. We want to minimize the cross entropy loss between these two, Z3 and Q3, and maximize it to all of those over there, right? That's basically the main purpose. And not cross entropy, cosine similarity, where we want to minimize the cosine similarity. So this goes ahead and almost does everything we want. There's still one more step. We're going to do sampled negatives, index, plus equals index times sequence length. Now, why are we doing this? So we have 99 samples, right? So we have 99 samples. So we have a batch size of 2. So the first sample goes from 0 to 99 steps, and the second sample goes from 0 to 99 steps. It's just we know that in this first sample, let's do it in orange, in this first sample, only the first 77 are valid, right? Are valid. When we compute our loss, we're actually going to flatten everything. So instead of having 2 vectors that go from 0 to 99 and then 0 to 99, instead of doing it like this, we're going to flatten it. We're going to go from 0 to 99, and then we're just going to concatenate it again, 0 to 99. Now, this is not helpful to us because, well, these indexes no longer mean anything in the list. What we should really have is the first sample goes from 0 to 99. The second sample goes from 100 to 199, right? So we're just gonna re-index it after we, as if we had flattened it. So the first sample will go from 0 to 99, which is what we have right here. It'll be at the first sample, index is 0, so it'll be plus equals 0. The second sample is gonna go from 100, right? Because it'll be 1 times the sequence. That's just gonna go from 100 to the next step. So we're just offsetting everything because we're gonna end up flattening it at the end. So we wanna make sure that our indexes still match. In this case, when we flatten everything, it's gonna end up, we're gonna have a batch size time, so our data, like as always, it's gonna be batch by sequence length by like the num negatives or whatever. We're gonna make it batch times sequence length by num negatives. But this means our negatives have all been flattened into a single list. We need to make sure we're grabbing the correct indexes, so we need to just essentially offset our index here just so it matches when we flatten it. And so finally, it'll look something like this: print sampled negatives. And I'll refer back to this again when we get to it. So you can see the first thing starts at 0, and we sampled all this stuff. The second sample will start at 99, and we've just offset everything by that, right? So it starts at 99. And so actually, one thing that I've done slightly incorrect here, there's 99 things. So this will go from 0 to 98, 0 to 98, right? Because it's 99 things, so 98, 98. That means this is going to go to 98, and then the next thing will go from 99 to 99 more things after that, dot, dot, dot. And so we're just offsetting everything just for the indexes to work out. So the first thing is all the indexes from 0 to 98. The second thing will be all the indexes from 99 to whatever. If we had more samples, then it'll just keep offsetting it over and over again, just so when we flatten it, it's all already prepared for us to work with, right? We could also have done this later, but it's just easier to do it here. So our sampled negatives is going to be torch.tensor sampled negatives. It was a numpy, it's convert tensor. We could have also just done this all in torch to begin with, but it's fine. Torch.long print sampled negatives. There we go. So we have sampled all our negatives. For every single sample, we have the corresponding negatives that we want to use for the contrastive loss. And so we are good to go. Return sampled negatives. And this was probably the most challenging part of the entire implementation, like at least most annoying part of the entire implementation. So we are now good to go here. All right, so that solves our utilities. Now let's work on our data loader, right? So let's actually work on the data set. It's where we're going to be putting all this stuff together. So let's do new file, dataset.py. All right. I'm going to go ahead and pull all these imports in. So we're just importing all those methods we just wrote, right? Subattention mask, sample negatives, span mask, Wav2Vec config. And then you have all this stuff here just for our actual setup. So we're going to do class, LibriSpeech dataset, and Endom, or not, and Endom module. This will be a dataset class. And let's actually import, let's copy this stuff in as well, just to make it easy. So I don't have to type all this. So we implemented this in the, let's pull it up again, LibriSpeech. LibriSpeech data is pretty straightforward. We have essentially all these splits. We have a test clean, test other, train clean, train other, train whatever. We have all these training splits. And so one of the splits, it has like a folder inside another folder inside another folder. And then we have our audio files. We have audio files, and then you have this text file that gives me the transcript for all of those audio files. So we already actually wrote a data loader for this in the deep speech architecture, so we're not going to spend as much time kind of working on this, but this should be relatively straightforward. I also did this. You can find this in the Git repo. I'm not going to implement this. I already created this file here called audio durations. That's fine. And this audio durations file essentially is for every single file. I have the how many seconds long it is. This is so I can pre-filter data that's too long because it would throw OOM errors, right? So like typically on most GPUs, anything above 20 seconds on a reasonable batch size will lead to a out of memory issue. So we can just filter out any samples. There are a couple that are longer than 20 seconds, and then anything that's shorter than 22 seconds, we can also get rid of that because it's just not enough data. And so what we're going to do is, and we can actually copy all this in as well, just keep it simple. So we have our sampling rate. So Wav2Vec2 trained on 16K hertz, and the LibriSpeech data is also 16K hertz, so we have everything there. We have how many audio channels we have, there's just one. And we're going to go ahead and truncate any audio. That's too long, so we have everything there. And we have our path to data route, so we can go ahead and load that right here. So our path to data, if name equals main, this is our paths to data. And so our data set will be the LibriSpeech data set path to data, right? And everything else can stay. That's fine. And so let's go ahead and start this. The first step is we just have a bunch of for loops. So we'll do self.LibriSpeech data, speech data. It's going to be an empty list. And we're going to do for split in include splits. So we're going to loop through every split. And that's going to be these, right? So the train clean, train whatever, right? So all of these splits that we had, dev clean, dev other, test clean, test other, train clean, train other, right? Those are my different splits that they offer. We're just going to use these for now, just to keep it simple. We'll loop through each one of them. So then the path to split is going to be os.path.join, and it's going to be path to data root and split, right? So that's it. And then again, remember, after we go in one, we have all these folders, and these are the speakers, right? Different speakers. We'll do for speaker in os.lister, just loop through all the speaker files inside path to split. Path to speaker is going to be equal to it'll be os.path.join, and again it'll be path to speaker and path to split and the speaker, right? So then we've done that. After we've gone in one folder, we have another folder. We have these sections, right? So we can do that. For section in os.lister path to speaker, we can then do path to section is going to be os.path.join path to speaker and then the section, right? So we've just looped through essentially our lists of, file and file and file. And now what we're going to do is grab our file. So files is going to be os.lister. So if we again check, inside one of these, we have all of these different files. So let's go ahead and do that. os.lister path to section. And our transcript file, it's going to be just the file that ends with text. So our transcript file ends with text, so we can do that. So it's going to be path for path in files if .txt, there's only one of them, in path. And because there's only one, we'll just grab it. So there we go. So we can print, actually it's really self-explanatory, we don't have to really look at this. Now that we have that, I'm also going to load that audio durations is equal to pd.read_csv os.path.join. It'll be the path to section, and it'll be the audio duration.csv. Right, so this is, again, very simple. I just wrote a method. You can find it in my Git repo. I just have these files in my thing already. You won't have it there by default, so you just can compute it and just save a quick CSV file that has the duration for every audio, just so we can use that. And we can convert this to a duration, or a dictionary. So audio durations dictionary is going to be audio durations dot, the index will be the root, right? So the root directory. And we're going to grab the duration, and we'll convert it to a dictionary, So if we do print audio durations dict, and let's throw a break, and another break, we should be able to see a little bit of this to see what's working, what's not. Let's look at our data set. Any bugs? So there you go. We have a dictionary of here's my file name, and here's my duration. Here's another file name, here's my duration. So it's just easy for me to grab the durations and filter out anything that is too long. Now we can open the transcripts with open os.path.join. It'll be the path to the section, and our transcript file, and we can open it in reading mode as W as F. Transcripts is equal to f.readLines, right? So we're going to load all of them. Print transcripts. And so we'll get a file that looks kind of like this, right? We have all of these things, and each one is basically a name, or a file name, and then a transcript, and then another file name, another transcript, split by these new line characters. So we have to just clean it up just a little bit. For line in transcripts, we can split line is equal to line.split. This is going to split every single line on whitespace characters, where I know the first thing is our ID, and everything else after that is our transcript, right? So we can just easily parse it. So our audio root is going to be split line 0, and then our audio file is going to be the audio root plus dot FLAC, right? Because these are all FLAC files. So that's the name of the audio file. It'll be 103.1240.0000.FLAC. That's the name of the file. That's just how they save it. And we can see that right here. It's the name, or it's the number .FLAC. Then we have the full path to audio, and this will just be os.path.join, and we're just going to stack on the path to the section, and we're going to add the audio file in there. And then lastly, our transcript is going to be just go ahead and rejoin all of the remaining text over. So it'll be the split line, but 1 to the end, because we're skipping that first thing, because the first thing was that. If we print out the transcript file, or not transcript file, just transcript, my bad. If we just print out the transcript, and throw a break in there, just so, don't need that. Let's go here. There's our transcript, right? No problem. There's also, you can't see it, but there's a new line character in here. So we can go ahead and just do .strip to clean all that up, and we're good to go. So now we have the transcript, and we have the corresponding path to the audio, which is all I need, right? That's all I need. So lastly, let's just check duration is going to be equal to audio durations dict. And we're going to grab for this specific audio root, right? For this specific audio file, what is the duration? And we can do if duration greater than or equal to min audio duration, right? We want to make sure it's at least long enough. And our duration is less than or equal to max audio duration or truncate audio. So if truncate audio is false, that means we're not truncating our audio. That means I need to make sure it's long enough. But if we are truncating our audio, then we don't really care how long it is. We can just go ahead and truncate a chunk, pull out the piece that we want, just randomly sample some chunk of it. Truncating audio is totally fine for the purposes of pre-training. Truncating audio will not work for fine-tuning with CTC, because if I cut out some of the audio, I don't know what portion of that transcript actually goes with that audio. So that's fine. For pre-training, we don't really care about the transcript, but for fine-tuning, we're going to care about it a little bit more. So now that we have all that, we're going to do self.LibriSpeech data.append, and we're just going to store some tuples. It's going to be a tuple of the full path to audio and the corresponding transcript. And that's it. That's going to loop through all of our data and produce all of these things. And lastly, we have this check up here, if return transcript, because again, during pre-training, we don't care about the transcript. We only need raw audio, which is what makes it self-supervised learning. So we're going to do, let's see, if return transcripts, then we can do self.tokenizer. Tokenizer is going to be the Wav2Vec2 CTC tokenizer. We're just going to use the tokenizer from Hugging Face just to make our life a little bit easier. HF model name. We'll go ahead and load that Wav2Vec tokenizer where we're using this specific model. We're going to write our own model, but we can reuse the tokenizer at least from them. Def len self. We can just return len self.LibriSpeech data. So however many samples are in there is the length of it. And then our get item. self index. This is pretty straightforward. We can do each tuple, right, contains the path to audio in the transcript. So path to audio and transcript is going to be self.LibriSpeech data index, right? Just grab it because we have a list of tuples. After that, we need to actually load the audio. So we need the audio, and the original sampling rate is going to be torch audio.load. It's going to be path to audio. And then we will have the num frames is equal to self.max audio samples, right? In case it's too long. Okay, good. And that's basically where the truncation is happening, right? So we don't want to load more than that. Okay, so now that we have all of that, we want to also make sure that our audio is 16,000 samples. So we can do that. So we can do if orig sr. So torch audio.load will tell us what the sampling rate is. We need to make sure that we actually are the sampling rate we want. So if it's not equal to, self dot libri, well, let's see. If it's not equal to self, what did I call it? Let's see here. I just called it sampling rate. Okay, yeah, easy. Okay, self dot sampling rate. If the sampling rate of my audio is not the sampling rate that I want, then I need to do audio is equal to torch audio dot functional dot resample, and we're going to resample our audio to the, here's the original frequency, will be the orig SR, and the new frequency will be the self dot sampling rate. We're going to go ahead and resample our audio. This doesn't really matter here. And here, this num frames actually, let's get rid of this. We can do if truncate, if self dot truncate audio. Then we can do audio is equal to audio. Ignore that dimension. We're going to only keep up to the first self dot max audio samples, right? Because max audio samples, because the number of samples we want is 20 seconds times 16,000 samples per second. So 320,000 samples. So this is me just doing the truncate right here. This is if truncate audio. So there we go. Okay, good. So now that we have all of that, we're going to do if self.num audio channels is 1, right? So which it should be. Then we're going to do audio equals audio.squeeze. Because our audio is going to come in the shape of 1 by sequence len, right? 1 by sequence len. And if we only have a channel of 1, we don't really need that one, so we're just going to get rid of that and just have a audio of shape sequence len. And that should be totally fine for us. Lastly, there is one step that they do mention, normalize. Let's see here. Norm, which part of you were in? Let's find the data preparation section. Introduction, model, feature, training, masking. I can't exactly remember where in the paper they said it, but basically they said that they pre-normalize all the data before it's passed in. It's in here somewhere, I just don't remember where it was. So we're just going to quickly do that. Audio is going to be equal to audio minus audio.mean. And then, just like when we always normalize anything, it's going to be divided by np.square root audio.variance, right? So we divide by the standard deviation. And just so we don't divide by 0, we're going to add a 1e minus 7, whatever, right here. So we're just, subtracting the mean, divide by the variance, so our data is 0-centered and roughly normally distributed, right? Hopefully. So that's just a standard scaling of the data. We're always going to do this for all of our samples. And lastly, if self.return transcripts, if we want to do it, then we actually need to prep our transcripts. Our tokenized transcript is going to be torch.tensor, and we're just going to do our self.tokenizer that we should have above .encode our transcript. Go ahead and load our transcript, and then the batch is going to equal to whatever input values is going to be the normed, and let's call this the normed audio, just so it's clear. We'll have our normalized audio, and then we will have our labels, which is going to be our tokenized transcript. Else, our batch is just input values, and it's going to be just the normed audio. And we return the batch. And that's basically it for our data loader, right? Or our data set. The data set will essentially just go in, grab a sample, and then it's going to load this stuff. So let's go ahead and see if we do batch is next iter data set, and not, this won't be batch, this will be sample. Let's just print a sample out to see what it does. Let's give it a second. It takes a little bit of time because it actually has to loop through all of those audios. But there we go. So we have our input values. These are the actual audio itself that's been normalized. And then we have their corresponding labels, right? So this is the tokens of the transcript that we want to predict if we were doing CTC. Of course, during pre-training, that's not true. We don't have any CTC. We're just training on audio. So we'll be setting this to false, right? So we would do return transcript is false, right? But same idea. It's going to do, oh, it looks like I'm missing something. Return transcripts, plural. Thought I pasted it. I deleted it. It's fine. So yeah, we're going to essentially return only the audio and nothing else. Because when we're pre-training, we don't need anything else. Good. So that's our setup. Now, what about all of the stuff that we just did? Span masking, negatives, attention, all that stuff. Now's our chance to actually compute that because all of this will just happen on those batches, right? This is why when we wrote these operations, we always assumed we're doing them on a batch so we can then apply them. And so let's go ahead and write our collate function. So this is going to be def Wav2Vec2 collate function for pre-training, right? We're going to pass in a config here. And this is going to be just a quick wrapper on a collate function. It's going to take a batch, it's going to return something, and we're going to return the collate function, or return the method here. And so now let's go ahead and set this up. First, our config is going to be the Wav2Vec2 config, everything default, right? Nothing changed. And then our loader is going to be the data loader. And let's do it this way. Let's get rid of all this stuff. Data loader. And it's going to take in the data set. Let's do a batch size of 4, right? Because we haven't written any of the logic to pad the shorter things to the longer things and all that. So this is where we're going to do all of that. And then our collate function will be the Wav2Vec2 collate function for pre-training. And this will just take that config. Good. So now when I do next iter loader, we can print out the batch here. And we should see 4 examples of samples come up. And just to make things go a little bit quicker, we're going to set this LibriSpeech data to only do the include splits. Let's just do a small split. Let's do dev clean, right? Just on a small split, just so things go a little bit quicker. Nothing changes otherwise. Okay, good. So we have a list of 4 different things. We see we have input values here, then other input values, more input values, more input values. So we're just going to loop through, stick it all together, get our batch loaded, and then we'll be good to go. So step 1, we need our batch audios is going to be equal to sample input values for sample in batch. Now, of course, each of these things will be of a different length, so we're going to have to set this up. First, our attention mask is going to be equal to, and this will be the attention mask at the audio level. We will compute the sub-attention mask at the convolved level right afterwards. So we'll have torch.once len audio for audio in batch audio. So we're going to loop through. Our attention mask will be 1 for all of these. They're all of different lengths. We haven't put it all together. So just like we did before, audios will be torch.nn.utils.rnn.pad sequence. Go ahead and take our audios, take the batch audios, do batch first is true. And we're going to do our padding value. Padding value is just going to be 0.0. Right? We're going to pad everything with zeros. And the attention mask will be exactly the same thing. Right? It'll be exactly the same thing. So we'll just paste that here and just replace attention mask and our attention mask. There you go. So if we print our audios and print our attention mask, we should see exactly that. Looks like we have a bug, input values. Let's see here. Print batch 0. Must have just made a small mistake. It's input values, plural. There we go. All right. Sorry, just misspelled it in our data set. So now we're good. Now this should work fine. There we go. So we have all of our data. We can see these have pads in them because they're shorter than the longest thing. And so the longest thing has no attention mask. Everything is 1, so we want to attend. But we have some zeros for the stuff that's shorter. So we're good to go. We now have our attention mask. Of course, this attention mask is not as interesting to us. We want the sub-attention mask. The sub-attention mask is going to be equal to the compute. Sub-attention mask will pass in the config and the attention mask. So print sub-attention mask.shape. Right, so this will be I can see my longest thing will be of length 624, right? So that's my sub-attention mask, and we can just go ahead and test it this way. We can see we have, again, 1s and 0s, 1s on the longest things, 0s on the shorter things, but this is now at the convolved level, because the original attention mask was at the, if we print the attention mask.shape up here, and then sub-attention mask.shape right here, you'll see exactly what I'm saying. We have the longest sequence had almost 200K timestamps in it, right, for our audio. After all the convolutions, that longest thing becomes 624, and we've identified which things in the output of the convolution are pad and which ones are not pad. So we're good to go. We now have everything we need for our sub-attention mask. After that, we need our span mask, right? This is us for the pre-training purposes. We want the, what spans do we want to mask out for the, for training, for the pre-training task. So we can do compute span mask. And like we implemented this, the shape is going to be the tuple. It's going to be the sub-attention mask.shape. We're going to have the mask prob will be the config dot masking probability. And actually, I'll just copy this so I don't have to type it all out. But all of this information, like the masking probability and all of that, I set it in the config. So in the config up here, we can see we have our masking probability, masking span length, minimum spans, everything that we've already defined. So we have all that right here now. So that's our span mask. Then we need to sample negatives. So again, I'll just copy this just so I don't have to type it. We have to sample negatives, right? So we wrote the method to sample negatives. It's going to take in the feature shape, how many negatives do we want, what indexes were selected to be masked, right? The span mask, and that's going to go ahead and sample negatives. And so now we can print our sampled negatives. And you'll see that it's set to do 100 negatives, right? That's what we want. Sampled negatives. There we go. So we can see we have zeros for the stuff that we don't care about, right? But then we have, these are essentially the negatives we want to sample. What you're seeing here is the first thing is 624 long, so it goes from 0 to 624. The next thing, or 623. Next thing goes from 624 to 1248, and then whatever, right? So that's how it is. It's just harder to see what's going on because the sequence lengths are longer and the number of things we're selecting for masking is longer. But everything's in there. So for every single mask time step, we have the indexes that have already been shifted by batch size because we're going to flatten it later. We have the indexes for the quantized embedding that we want to use as negatives. And we also know that the correct answer is the index that we're at. So it should be easy to put it all together. And so lastly, I'll just copy this too, just put it all together. We have our batch, right? So we're going to go ahead, grab our input values, attention mask, sub-attention mask, mask time indices, sample negative indices, put it all together into one nice batch and return it. And that is our data loader, right? Very, very, very simple. Good. So now that we have written our data set, it is finally time that we get to write our model, I believe. So let's go ahead and start that. So we're going to write a new file, model.py. Okay, let's go ahead and now actually implement the model. To do this, it's relatively straightforward. It doesn't look all that different from a standard transformer model. So we're just going to start at the top and work our way down. The first thing we're going to need are some convolution layers. We're going to test with data in a bit once we actually get there, but for now let's just start writing these layers. So we're going to do a Wav2Vec2 layer norm con layer, right? And then dot module. We're going to try to follow the definition of the paper as close as possible. So we'll have self, we'll have our in channels, we'll have our out channels, we'll have our kernel size, we'll have a stride, and we'll have a bias, right? Bias is, it'll be a Boolean of true or false. And it'll be super.init. And we're going to do self.convolution. It's just going to be a simple con1d. It'll be in channels equals in channels, out channels equals out channels, kernel size is kernel size, stride is stride, and bias equals bias, right? So we've gone ahead and defined one of the convolutions. Again, remember, in our Wav2Vec architecture, we're going to have our convolutional encoder. It's not just one convolution, it'll be a stack of convolutions as defined here. So we'll have 1, 2, 3, 4, 5, 6, 7. So we'll have 7 convolutions. We have their dimensionality, we have their strides, we have their kernels. So we're going to go ahead and define one of them here and then stack them on top of each other to get all the different convolutions. We'll do self.layer norm. It's going to be nn.layer norm, and it'll have the out channels as the embedding dimension. And then lastly, self.activation is nn.glu as defined in the paper. They use the glu activation. So we can do a forward self x. Now in our convolution, convolutions expect this data in the shape of batch by channels by sequence length. So the length should be the last dimension, and that's how our data is going to be passed in. So we're going to do x is equal to self.conx. Layer norm, on the other hand, expects data to be in the shape of batch by length by channels, or the embedding dimension. So we need to do x equals x dot transpose minus 1, minus 2, flip them around, do x is equal to self dot layer norm x, and then again x is equal to x dot transpose, just put it back how we found it, minus 1, minus 2, minus 2. There we go. All right, so now that we have that, finally, after we complete our convolution, we want to do a activation. So x is equal to self.activation x, return x. Very simple. So it's just a convolution layer with a layer norm and an activation function tossed in. So now we can actually define our feature encoder, class Wav2Vec2 feature encoder, and this will be again nn.module def init self. This is going to take a config file, right? That'll define, and this config file is again all this stuff right here, defining the structure of the model of these convolutions. Self.config is config, and what we're going to do is assert. Just a quick check, right? We want to make sure that the number of convdims, constrides, and kernels we provide, right? So the length of this, length of this, length of this, we're gonna make sure they're all the same just for sanity check purposes. And once we have verified that, then we can go ahead and write num con blocks is going to be just the len of config.kernel size. It doesn't really matter, or not kernel size, but con kernels. We have 7 convolutions in our case that we're going to stack on top of each other, so that numCon blocks would just be 7. And our conv channels is going to be, remember, right now it's all 512. Everything's 512. But for the first convolution, it's going to start at 1, right? Our audio is just a 1-channel input. So it's going to go from 1 to 512, then 512 to 512, 512 to 512, 512. Just repeat that over and over again. So we're just going to add that on. We're just going to add a 1 tuple onto the tuple, just make sure it's a tuple, it's already a tuple, but that's fine. Config.condim. So that'll create a list of like 1, 512, 512, 512, 512, dot, 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 right? Just like that. And what we can do now is self.conlayers is nn.module list. Right? It's just a list of these convolutions. And we're going to do for con index in range num con blocks. We'll do self.conlayers.append, and I spelled append wrong, append, here to you. Okay, and it's just going to be this Wav2Vec layer, right? So I can just go ahead and copy this part in, just don't have to type it out. we're just going to append on all of these. It's going to be a bunch of these Wav2Vec layers that we just created up here on top of each other. And they'll go from convindex to convindex plus 1, because it goes from 1 to 512, 512 to 512, right? So it's just the next one over. We'll have our kernel size, we'll have the stride, and whether or not we want to bias, and all that's set in the config, right? So there we go. After that, we need to write our forward method. Pretty straightforward. Self, we're going to pass in x, and what we're going to do is x for layer, layer in self.conv layers. We're going to do x is layer x return x, right? So it's me taking my audio and passing it through all of these different convolution blocks. And this gives me essentially everything I need for my feature encoder. Now that we have that, there's one important detail that we still need to look at, and this is our position encoding. So we can see here, instead of fixed positional embeddings, like doing sine cosine embeddings or maybe a learnable positional embedding, they use a convolutional layer which acts as relative positional embeddings. We add the output of the convolution followed by a GLU to the inputs and then apply layer norm. More specifically, they use a grouped convolution as per their actual implementation. So we're going to do exactly the same thing. New class, Wav2Vec2 positional conv embedding, and end.module, def init. And this is again going to take self, config, self.config equals config. Let's just store it there. And now we have our convolution. This is going to be our positional embeddings, right? So self.conv is equal to nn.conv1d, and this is going to take config.embedding dimension, and it's going to go to the same, right? We don't want to change the number of channels. So again, embedding dimension. After that, we'll have our kernel size is config.conv positional embed kernel size, which I can't remember off the top of my head. I believe it was, yeah. So we're using a kernel size of 128, and we're using 16 groups in our grouped convolution, right? So there we go. And then we'll have our padding is going to be equal to config dot conv positional embedding kernel size divided by 2. This way the shape doesn't change. So we have the, we could have also done just padding equals same. It would give you the same result. And then we have our groups. So it's a group convolution. So groups is equal to config dot, there we go, positional embed groups. And so lastly, we have our self dot activation, again, nn dot GLU activation is what they use. And so our forward method, very simple. We're just going to take our data and pass it through this thing. This is going to be, in this case, our data, when we pass it into here, it's already like at the stage for passing into transformers, which means it's going to be in the shape of batch by, like I mentioned, sequence length by embedding dim. But convolutions want the embedding dim first and then the sequence length second. So we just need to do a quick transpose. X is equal to x dot transpose 1, 2. Or -1, -2, but same thing, right? So that's our data. We're going to compute our positional embeddings. Positional embeddings is going to be self.conv x. And then we're going to go ahead and clip off any excess positional embeddings, right? So in our sequence length here, let's see. We technically shouldn't need to do this, but I guess if this isn't set to same, then maybe it can happen. I guess divided by 2 may not necessarily give you exactly the same output length, depending on what kernel size you pick. So this is more of just a sanity check. So we can set batch size by sequence len, len by embed is equal to x.shape. And what we're going to do is to look at these positional embeddings, and if for some reason it ends up being longer, we're going to go ahead and just only keep up to the sequence length that we wanted. So position embeddings is equal to position embeddings. For every batch, for every sample, we want to keep up to the sequence length, just to keep it always the same, but this shouldn't change anything if this was set to same, but we're going to keep it the way they did it. That's fine. And then our position embeddings is going to be equal to self.activation, position embeddings. And then again, position embeddings is equal to position embeddings.transpose, put it back how we found it. Retranspose it back to batch by sequence by embed dim. and we can return our position embeddings, just like that. So this is how we compute our positional embeddings just defined by the paper. Go ahead and apply a grouped convolution on our data, and then we can go ahead and add that back in the next step. So we can now finally do our Wav2Vec2 encoder layer. So let's go ahead and do that. So we're going to write the class Wav2Vec2 encoder, and this is skipping ahead a little bit, but that's fine. Wav2Vec2 encoder. This is what's going to have our convolutions and our, it's going to also have our transformer, which we haven't written yet, but we'll get there, so that's fine. And then dot module, def init, self config. And this is we're gonna add more to it, but for now let's just focus on our thing that we're working on. So the first thing will be self.config, just go ahead and store that, equals config. And we're gonna do self.pos.conv embed is going to be Wav2Vec2 positional conv embedding with this config. So we've already defined that. And we have self.layer norm. We'll need a layer norm after this. It's gonna be nn.layer norm. It's going to be config.embedding embedding dimension. Embedding dimension. And then we will have our self.dropout, right, for dropout purposes. It's going to be nn.dropout config.conpositional embed drop p, which I also defined in here, right? My dropout probability on my convolutional, the positional embeddings essentially. So we have all of that. And then we have our encoder layer. So let's go ahead and define our feature projection, feature extractor stuff first. So what we're going to do is set this up. We have our Wav2Vec2 model. Let's write one more thing, class Wav2Vec2 model, and then module, def init, self config. So I'm just writing a couple models in concurrently, just so we can see how it all fits together. It'll be a little bit easier once we get through one of these examples. So super.init, and then we're going to do self.feature extractor is equal to our Wav2Vec2 feature encoder config. And then we'll have self.feature projection, and this is something we haven't written yet, Wav2Vec2 feature projection config. Okay, so we should probably write that right now. And then after that, we'll have the self.encoder is equal to Wav2Vec2 encoder config. And we've written that. So the feature projection, what is this? Remember our Wav2Vec, the convolution will output a embedding dim of 512. Our transformer expects an embedding dim of 768. So we need to do that mapping, right? We need to go from our input 512 embedding and project it to the 768 that we need. This is very simple. It's just a linear layer that just does that projection. So let's just go ahead and add that in up here real quick. So class Wav2Vec2 feature projection, and then module def init self config, and this is going to be very simply self.config equals config, store that there, and it's going to be first a linear layer. Self.projection is going to be nn.linear. It's going to take config.convdim -1, and it's going to project it to config.embedding dimension, right? Embedding dimension. So it's going to go from the convdim -1, which is 512, and it's going to project it to 768. But of course, we're going to throw a layer normalization and a dropout in here as well, so we can do that. So self.layer norm is nn.layer norm config.convdim -1. They normalize it before we provide it to the projection layer. So you basically layer norm the output of the convolutions. EPS is I don't know, 1e -5, but that's fine. We'll just ignore that. I think that's the default anyway. And then we have a dropout, right? Self.dropout is nn.dropout, and this will be a config.feature projection dropout p. There you go. And so def forward self x. All we're going to do is take our data. We're going to first norm it. Normed x is going to be equal to self.layer norm. So normalize it x. And then we'll do projected x will be self.projection normed x. And then projected x is going to be equal to self.dropout projected x. And then we can return, and this is one key part, return both the projected x and the normed x. Now, why do we care about this normed x? Go back to the figure. Remember, the output of this convolution has two tasks. The first one is going to go to the quantizer. So we'll pass the normed outputs to the quantizer to do our vector quantization. We will then pass the projected outputs, that went from 512 to 768, to the transformer. So the normed x will go to the quantizer. The projected x, where'd it go? The projected x here will go to the transformer. And so we have everything we need there. We have our projection layer. We have this. So let's go ahead and write our forward method. So this will be our Wav2Vec2 model. This should be relatively straightforward. I'll just copy this part in, just don't have to type it out. So our forward method is going to take all the stuff that we need. It'll have input values, the attention mask, the sub-attention mask, what time steps were selected to be masked for the purposes of pre-training, and then do we want to return the features to quantize, right? So we have that as well, and we'll see where all of this fits in as we implement it. But the first step will be we need to we need to extract features, right? So we're going to extract features. It's going to be equal to self.featureExtractor input values, right? Just like that. So let's go ahead and start paying attention to the shape. So these are there from before. We're going to do the Wav2Vec2 model for now. So model is the Wav2Vec2 model. Config equals Wav2Vec2 config. We're going to just do it on this tiny data. So we're going to grab a batch and we're going to pass it in. And all we're really going to be passing in is all of this. This should work, but it might throw an error. So let's just check real quick. Python model.py. Okay, so let's fix that first. Num-conv blocks. This should be kernel. Anything else? Okay, I'm missing a super somewhere. It looks like here. .init. What else? Missing another super on the feature projection. So let's fix that. Feature projection right here. Okay, missing another one on the actual Wav2Vec2 model. Wow, I missed a lot of them. Wait, no, that's weird. I have it right here. Oh, it's the positional conv embeddings up here. So that'll be these positional embeddings. Again, always forget this. Okay. And we have our Wav2Vec2 encoder. This will be right here. Okay, good. So we are making progress. There's some stuff in here that we don't need. So I'm gonna just, for now, throw an extra thing in there that we don't need just to handle any extra stuff that's coming from our dictionary that we don't really need for the model, but we do need for pre-training. So this will just kind of catch them and hopefully let me ignore them. Looks like we have some bugs. Expected input to have one channel, but got two instead. That's very interesting that we have multiple channels. So we have, let's see here. Let's print our batch. And we really want to look at the input values. Maybe we just got something kind of wrong. And let's comment U out. So we have that. Let's look at the shape. Input values dot shape. it should be, yeah, so it's 2 by this. It needs to be 2 by 1 channel by that. So in our data set, we need to make sure we add that back in. So let's add a, let's see here. Okay, let's just check here. We have this, we can do on our input values, we can add a dot unsqueeze 1, right? So that'll add a extra dimension in there. There we go. So that's our data now. Okay, good. And there's a random print in here that we don't need, so we can get rid of that. Okay, this should work now. So let's give this a test. Okay, good. So that's looking promising. So let's look at the print extract features dot shape. So it should be a 2 by 512 by 292. So we can see this has been compressed down, and we have 512 embeddings, right? So that's the embedding dim of every time step. Good. So now that we have all that, we can go ahead, after we extract our features, the next step will be to pass it through our feature projection, because we want it to have, we want to match it to the whatever the transformer expects to have. So we need to project our 512 up to the 768. So to do this, we already wrote the feature projector, so it's pretty straightforward. So we can do our, here we go, extract features. First of all, extract features dot transpose 1, 2, because everything we're about to do now expects these dimension of batch size by sequence length by embed dim. So we're going to flip those around. And then we're going to first grab our sub-attention. So this is sanity check stuff. So if sub-attention mask is none and attention mask is not none. So if we passed in a an attention mask but didn't pass in a sub-attention mask, that means we can compute the sub-attention mask from the attention mask. So we should do that. So we can do sub-attention mask is equal to this same as before, compute sub-attention mask, and we're going to pass in self.config and the attention mask and do .to input values .device, just to make sure it's on the GPU when we do it correctly. Input values .device. There we go. And so now our hidden states, so these are the outputs of the convolutions, and the extract features, which is just the normalized outputs that we did right here for the feature projection, right? We have the projected x and the normed x, so those will be our hidden states and the extract features. It's going to be equal to self.feature projection, and we're going to pass in here extract features. So we have print hidden states.shape and extract features.shape. And basically one should be of the dimension of 768, and the other should be the dimension of 512, right? So we can see that right here. And this one's going to go on to do our quantization, and this one's going to go on to the transformer. So we'll see all that work out in a bit. Good. So next up is we have our, if the span mask is provided, then we should randomly replace, we should replace our tokens here with those mask tokens. So essentially, we have our data right here. We selected things to be masked. We should actually replace them with the mask token. We actually don't have a mask token yet, so let's go ahead and add that in. So we're going to do if config.masking probability greater than 0.0, right? We're going to do self.masked spec embed. So this will be our mask token. Will be just a learnable parameter with, I'll just initialize it as a float tensor, empty float tensor right now of the shape config.embedding dimension. Right, so we're going to go ahead and initialize that, and we'll do torch.nn.init.uniform initialization, self.mask spec embed. So we're going to uniformly initialize this mask token. We're going to now fill it in. We're going to fill it in. So we have our print, our hidden states.shape, and we have our mask time indices, time indices.shape. And if we look at this, it'll be pretty clear what's going on. We have our data that's in the shape of 2 by 292 by 768. And I have a true-false mask here where true identifies which of these embeddings of length 768 do I want to replace with my mask token. So let's go ahead and just do that. Our hidden states. at these mask time indices, we want to set it to self.masked spec embed, but we need to make sure it's the correct d type. So we're going to do to hidden states.dtype before we copy it in, right? We want to make sure we copy it in with the same data type because we'll be training in bfloat 16 anyway, so we'll see that in a bit, be useful. And so now lastly, we need to write our encoder. So now is the time for our Wav2Vec2 encoder. Let's go ahead and write the forward method for this encoder, and then we'll go from there. So we're first going to do def forward self, and this encoder is going to take essentially a lot of the, it's just going to take x and the attention mask, which in our case will be the sub-attention mask, but that's fine, the attention mask, which we'll just set to none by default. And so this encoder is going to be both for the transformer and our positional embeddings. We still haven't done the positional embeddings. So that's why we have that defined up here. Let's go ahead and add those positional embeddings in. So position embeddings is going to be equal to self.pos conv embed x. X equals x plus positional embeddings. X is then, so this is me computing positional embeddings, adding them into my data, just like they said in the paper. Just add the output of the convolution in, giving me relative embeddings. Then x is equal to self.layer norm x, go ahead and renormalize it, and then x is equal to self.dropout x. So just as we had defined everything. But of course, this is not the only thing we're going to do in the encoder. The encoder also has all of these transformer blocks, right? Transformer blocks. So let's go ahead and define our transformer. Defining the transformer will be basically like every other transformer that's out there. There's nothing fancy. It's going to be an attention mechanism and a feedforward layer, and that's it. So we can quickly write this. I'm already assuming you already know about transformers and how to implement them. If you don't, just go ahead and watch those previous videos. But we can go ahead and do that. So we have our Wav2Vec2 feature encoder. Let's see here. Feature encoder. Let's just start sticking them right here. And actually, let's do it. Doesn't even matter where we do it. So let's just do it right here before the encoder. So our new class, Wav2Vec2, and the first thing we're going to need is a let's see. First thing we're going to do is our attention, right? So Wav2Vec2 attention. It's standard encoder attention, right? So bidirectional attention, nothing fancy. So self config, and we're going to have self.config is config, and we're going to throw in our, like always, it's multi-head attention. So self.head dim is going to be config.embedding dimension divided by config.num attention heads. And then we'll have self.qproj is nn.linear config.embedding dimension to config.embedding dimension. And our q, k, and v are just 3 of the exact same layers, so we can go ahead and copy those in. So it'll be qproj, kproj, and vproj are 3 projection layers. And then we'll have our final output projection, right? Because we're going to do multi-head attention, we need all the heads to get to know each other. So self.outproj is, again, another one of these layers. Very straightforward. Now that we have that, we just write our forward method, forward self x and the sub attention mask, which we'll call attention mask here. And this is going to be batch by sequence len by embed dim is our x.shape. And we're going to do q is self.qproj. And we're going to pass an x. But we're going to, again, like always, we want multi-head attention, so we're going to reshape it to batch by sequence len by self.config.num attention head. So how many heads of attention do you want? By self.head dim, right? So I'm going to take my embedding dim and split it into number of heads by the dimension per head. And then we'll transpose these last 2 dimensions, or these dimensions, sequence. So it becomes batch by num heads by sequence len by head dim. And we'll just repeat this again. Q, we'll have our K, and we'll have our V, and that'll come from the Kproj and the Vproj, but everything else is the same. So this is our standard attention setup, nothing new. And once we've done that, we want to compute attention. We could write the attention mechanism, but might as well just make advantage of flash attention. So attention out is going to be f.scaled.productAttention. Here we're going to pass in qkv, because that's what it wants. It wants the attention mask is going to be our attention mask that we write here. And the dropout p is going to be self.config.attention dropout p if self.training else 0. So during training, we're going to use the dropout. If we're not training, then we're not going to use the dropout. Once that's done, we're going to take our attention out and just put it back. So we're going to have to, we transposed 1 and 2. We're going to transpose them again so they're back to the same shape. So it'll be attention out dot transpose 1, 2, and then dot flatten 2. There we go. Go ahead and flatten it. So we're back to batch by sequence by Embeddim. Standard setup. We're going to project this. Attention out is going to be equal to self.outproj attention out. Get all the heads to know each other because the heads were computed in parallel. And we can return attention out. So this is our very standard setup, standard attention. There's nothing fancy in here, right? So if you already are comfortable with transformers, nothing in here should be new. Similarly, we can do our Wav2Vec2 feed forward nn.module. And honestly, I won't even bother typing this because there's nothing in here. It's just 2 linear layers, so I'll just paste it in. There's nothing fancy here. This feedforward layer is just, it's going to take an embedding dimension, project it to the MLP ratio. We have a linear layer that goes from 768 to 768 times 4, activation, a dropout. Then we're going to go from, to basically just go back the other way around, 768 times 4, back to 768, another dropout. Stack it through the layers, just standard MLP module for attention computation, right? So this means we can write our encoder layer, class Wav2Vec2 encoder layer, nn.module, definite, self, config, and I'm actually forgetting again. There should be super.init right here. Probably didn't forget another one, but it'll complain if I do, so it's fine. Super.init. And this is going to be just a standard attention block. Self.attention is going to be Wav2Vec2 attention config. And then we'll have a self.dropout on the attention nn.dropout. This will be config.transformer encoder dropout, which I've already set in the config, right? So whatever probability it is. And then we'll have a layer norm. Layer norm is nn.layer norm. The embedding dim will again be config.embed dimension. Then we have self.feed forward. This will be the Wav2Vec2 feed forward layer that we just wrote. Config, the stack of 2 linear layers. And then we have our self.final layer norm is nn.layer norm, and again config.embedding dimension. Right? Nothing fancy. And then this will be the standard forward method for all transformers. We're going to take x, this will take the attention mask, which will set to none. And x is going to be x plus, because they're residual connections, self.dropout, self.attention, and we're going to pass in x and the attention mask. And then x is again self.layer norm, go ahead and normalize it. And then x is again x plus self.feed forward, feed forward x, and then again x is equal to self.final layer norm x, return x. So this is our standard transformer block, right? Nothing fancy. So we can now use this in our encoder. So this is going to be in here. We need to define, so this is all of our convolution and positional embedding and all that sort of stuff. So the encoder will essentially take, so we've already computed here our feature projection and extraction. So these are our convolutions. Now we're going to pass those embeddings, at least these hidden states, to our encoder, right? So we need transformer blocks. We're going to do, let's see, self.layers is going to be nn.module list. It'll be our Wav2Vec2 encoder layer config for blank in range config.num transformer layers, right? So we're just going to stack all these layers on top of each other, And this should be relatively straightforward. So one thing we need to do is, because we're using flash attention, our attention mask right now is in the shape of, it's in the shape of batch by sequence length, but flash attention expects it in the shape of batch by 1 by sequence length by sequence length. So we've talked about this transformation before in previous videos when we implemented the transformer. So we'll do exactly that. So what we're going to do is, if attention mask is not none, we need to just process it. So first, attention mask is equal to attention mask dot bool, just convert to a true false thing, just in case it wasn't already. And then here's an option. We don't really need to do it. Anything that's selected to be, or anything that's basically false in our attention mask, so things we don't want to pay, we don't want the transformer to attend to, then our values in the original data, we can technically do this. We can do attention mask is 0. So what I'm saying is, if we have some data here where we have these embeddings, right? And then we have another one right here. And then we had some padding right here. Remember, these, I know these are pad tokens because I know the output shape of the convolution. So I know that these two are not a part of the actual data. But because they were a part of the convolution operation, these things have some values, right? They're going to be something. It's just when we attend to them, these will be ignored. So it doesn't really matter. So technically, we can just go in and set these to just 0 vectors, right? Because it doesn't matter. Even if we didn't do it, it wouldn't change anything. But it's just good practice, so we'll throw it in there. So anywhere where the attention mask is false, so if you flip it, it's true, we're going to set it to 0, right? So wherever we don't want to pay attention to, we're going to just make those vectors 0 because they don't matter. Good. And then lastly, attention mask is going to be equal to, so attention mask, remember, it's batch by sequence. So we're going to add a dot unsqueeze 1 dot unsqueeze 1. So this is going to make it batch by 1 by 1 by sequence. That's the shape now. And then we're going to repeat this dimension, sequence length, number of times, just so we can get the final shape. So 1 by 1 by sequence length by 1. And this is going to be batch by sequence length by embeddim is x dot shape. So this will reshape it from batch by 1 to sequence length to just batch by 1 by sequence length by sequence length. And the only reason we're doing this is because this is how the flash attention expects it. Otherwise, we wouldn't bother. And so now that we have our attention mask, we've computed our positional embeddings. We've added that on. So now it's time to do the transformer for layer in self.layers. We can do x is equal to layer x attention mask equals attention mask, right? So that's it. That's me passing my data through all of these transformer blocks. And that goes ahead and wraps up the actual Wav2Vec2 encoder. So we can go back down here to the model and wrap up this part as well. And then we can start on the stuff we need actually for pre-training. So this is going to be our Wav2Vec2 model. It's our base model. And this base model is what we're going to load into our Wav2Vec2 for pre-training or for CTC loss, right? So it's going to be like our kind of fundamental base model that we're going to need for all the future stuff that we'll write. So we have our hidden states. We've gone ahead and replaced, and this will be if mass time indices is not none, right? So if we actually have it, then we're going to pass it in and replace it like that. And then we will do our encoder outputs is equal to self.encoder. So we wrote the encoder. It's all of this stuff that we just wrote up here. Encoder. And we're going to pass in the hidden states, which have already been projected to the correct size. And the attention mask is equal to the sub attention mask, right? Because all of this is happening at the convolve level. And now what we're going to do is if return features to quantize. So if we want to actually, which for pre-training we need the features to quantize, we're going to return back our encoder outputs, right? So the output of the transformer, as well as our extract features, right? Extract features, which we're going to, or not extract features, sorry. Yeah, this extract features right here, which we're going to need to quantize. We haven't done that yet. Otherwise, we're just going to return our encoder outputs, because when we train for CTC for like transcription, all we really care about is the encoder outputs. So that's what we have. Good. So now, finally, Wav2Vec2 for pre-training. This is the hard part. Wav2Vec2 for pretraining nn.module definite self, and this will be again passing the config super.init self.config equals config. Scroll down just a little bit so it's easier to see. And then we're going to have our models, right? Self.Wav2Vec2 is going to be the Wav2Vec2 model that we just spent all this time writing, right? So there we go. That's our entire convolutions and everything else. And then we'll have self.dropout features is going to be nn.dropout, and this will be config.preQuantizer dropout. So again, we've defined all this stuff in our config. So we have our quantization before dropout. Now we're going to have our quantizer and everything else. So we're going to have to work on that. Let's go ahead and start with this, our forward method, def forward self x. And actually this won't be just x, it'll be, I'll just copy this in. This will be everything, right? Everything that we care about. There we go, everything. And so now what we're going to do is two things. First, we don't need kwargs here anymore. Let's see, where did I, right here. We don't care about you anymore, so we can get rid of you. That was just to let it work. And then for you, we can enable you and turn off, delete you. And we want the Wav2Vec2 for pre-training. There we go. So step one, we want to compute our transformer outputs. So let's start with that. If masked time indices is not none, right? So then we're going to make sure masked time indices is equal to masked time indices dot to torch.bool. Just always make sure this is a boolean because it should be, because that's how we pass it in, but just in case. Now what we're going to do is use our Wav2Vec model, which is going to return both the encoder output and the extracted features. So our transformer outputs and features to quantize is going to be self.Wav2Vec2, and we're going to pass in the input values, the attention mask, the sub attention mask, our mask time indices, and return features to quantize is true, right? We do want to return our features to quantize so we can quantize them. We just haven't done that yet. And so that's everything we need for our setup. Now, here's the key idea. Our quantization is going to happen at a lower dimension. So let's just go ahead and write our quantizer first, and then we'll come back to the rest of this. Okay, so our Gumbel-Max, so this will essentially, let's go back here. Quantization is done through the Gumbel, right? So quantization is done via Gumbel-Softmax. I have an entire video covering exactly what Gumbel-Softmax is if you want to know some more details, but we'll kind of go over it in a speedier way this time. So let's go ahead and start implementing that. We'll have class Gumbel, or let's do Wav2Vec2 Gumbel vector quantizer nn.module def init self config, and there's going to be a super.init like always. Okay, so step one is one key thing is this quantization doesn't have just one codebook, it actually has two codebooks. So there's two codebooks that we're going to be using. So we're going to do our self.numGroups, which is how many codebooks we want, is going to be config.num codebook groups. And then our self.numBars, which will be the number of codes per quantizer, per codebook, is going to be config.num code vectors per group. So in our implementation, there's going to be, as we can see, there's going to be two code books, and each code book's going to have 320 codes in it. So that's exactly what we're going to be using, right? That's how we're going to set it up. And so let's go ahead and define this. And this is where it becomes a little bit interesting. in the implementation. So let's just draw it out just to make it clear. What we want is to have two separate codebooks. We're going to have one codebook like this, and I'll have some embedding dim by number of codes. And let's just write exactly what it should be. It should be 320. That's what I want it to be. And then I'm going to have a second codebook that also has the same embedding dim and another 320 codes, right? And instead of having two different codebooks, what we're going to do is just concatenate them together. So we're going to create one big codebook with 640 codes, right? So it's going to be embedding by 640, and then we'll cut it up later, cut it up afterwards. So let's just do that first. So we're going to do self.codeVectors is going to be equal to nn.parameter, and we'll do again torch.float tensor. Just go ahead and initialize. It's going to be in the shape of 1. That's just dummy dimension. Self.numGroups times self.numVars, which will be 320 times 2, which will be 640. And then we'll have the config.codeVectorDim divided by self.numGroups. So here's the other key idea. In our setup, we want our final code vector dim to be 256. But if you remember again, in our Gumbel-Softmax setup, here they say that they do a concat. So what they do is we product quantization to choose quantized representations and concatenating them. So what we do is we choose one entry from each codebook and concatenate together the resulting vectors, right? So what we're going to do is we're going to select a code from here and then select another code from here. Oh, my bad. Another code from here. Take both of those codes and like concatenate them on top of each other. I want the total length of this to be 256. That's my codebook dim that I want. So each one of these must be 128, right? For that to work out. And so for that exact reason, when we look right here, going back to the model, that's why you have code vector dim divided by numGroups. It's 256 divided by 2, because when I take my two 128 dim vectors, put them together, it's now a 256 dim vector. Good. So that's it. And the last thing we need is we need to actually project it. We want to project from, and we'll see what this is in just a second. This will be self.waitProj. It's going to be nn.linear config.condim -1. And we're going to go to self.numGroups times self.numVars. So what exactly is going on here? We have 640 things here that we want to pick from. And we want to pick two things, and we'll see how that works out in just a bit. But what we have is an embedding, right? We have some embedding here of length. In our case, it'll be 512, right? That's the output shape of our, the output embedding dim of our convolution, right? Because we'll be doing this on the non-projected to 768. This is just the raw output that's been normalized from a convolution. We have 512 here, but we have 640 possible codes we can pick from. So why not do a linear layer that takes 512 in and outputs 640 things, just like a classification layer, right? We have 640 options, so project it to 640, and that's it. We're just going to be projecting our each embedding individually to 640, so then we can pick our sample that we want. And the way we do that is the Gumbel-Max, and we'll get into that in just a second. So let's go ahead and just keep going. This will be that layer that takes the output, basically takes the embed dim and projects it to the 640. And then we have a self.temperature. We'll set it to 2. Temperature is our Gumbel-Softmax temperature, and we'll see how that is implemented in a bit too. So first, def forward self x, right? And this is gonna, let's just keep it the same. We're gonna have hidden states, and we're also going to have our mask time indices, which will set to none by default. And so what we're going to do is our batch size by sequence length by hidden size. It will be the hidden states dot shape, right? That's the expected shape for our data. And what we're going to do is project our hidden states. So our hidden states will be equal to self.waitProj hidden states. And it'll be good to actually follow the shape here. So let's set it up a little bit. let's do in our config, I set the number of transformer layers to be pretty small, so it's easy. So if we do print features to quantize.shape, let's just verify this. We should have, okay, looks like we have a bug. We should fix these real quick. We have for Wav2Vec encoder has no attribute layers. Let's just check. Wav2Vec2 quantizer model encoder. For self.layers, there we go, my bad. And we have our, there we go, so we have 512. So we have batch size of 2 by 292 by 512, embed them. Good. So this is what we want to quantize. So let's define our quantizer here. Self.quantizer is going to be a Wav2Vec2 Gumbel vector quantizer config, right? And yeah, that's it. So that's our quantizer. And so what we're going to do is quantize these, right? We're going to do self.quantizer. We're going to pass in our, let's see here, the hidden states and the mask time indices. So it's going to be the features to quantize, the things we want to quantize, and the mask time indices. And there we go. All right. So now, if we print our hidden states.shape before, and then print our hidden states.shape afterwards, you'll see that we had a, oh, looks like we have some typos here. Num groups is num groups. Num codebook, oh, it should be code vector, sorry, code vector groups. And we're good. Okay, so each embedding was 512. We've mapped each of these embeddings to the 640 possibilities for our Wav2Vec codes, right? The 640 codes that we have to pick from. Good. And now what we're going to do is, of course, we don't want just one of them. We have 2 codes. So we're going to do hidden states is going to be equal to hidden states dot reshape, and we're going to put together batch size by sequence length. So it's going to be batch time sequence length times our number of groups, self.num groups, and then -1 for the rest of the dimensions. And this will give us hidden states.shape. You'll see we're now at a 1168 by 320. So we have basically 320 code vectors, and we have 1168 samples, right? Samples. We have batch times sequence by number of code books, and each code book has 320 things. Nice. So now that we have that, we need to set up the rest of it. We're going to do if self.training. So during training mode, then we want to compute derivatives and do all of that. So the purpose of Gumbel-Softmax is that it enables us to sample from a distribution while making it differentiable, right? So I have the whole video talking about that, but we have exactly that. We have some raw logits. We have 320 values here, and if we just took the argmax, like we do in a classification problem, right? This is basically a batch size by number of classes. If you think about an image classification problem with 320 image classes, you pick the image class with the largest sample, right? The largest value here. It's just argmax is not a differentiable function. So we could instead use Gumbel-Softmax to sample from this distribution. So for example, we print hidden states, and let's just look at one of these hidden states. So this is going to be actually just 0, my bad. So these are my raw logits. We have 320 logits right here of things we can pick from. And technically I could do a torch.softmax axis is, or dim equals -1. That converts my logits into a probability vector, and I could pick the argmax, or I could sample, right? I could do torch.multinomial, and that'll say 0.14% of the time I'll get this, 0.26% of the time I'll get this, 0.24 I'll get this. So I could also technically just do a multinomial sampling. The problem is, again, multinomial sampling on this probability distribution is not differentiable. So our Gumbel-Softmax trick allows us to sample from this distribution as if we were doing multinomial sampling, but in a differentiable way, because we're using the reparameterization trick. So our code vector probs, right, probabilities, is going to be nn.functional.Gumbel-Softmax hidden states dot float. We're going to make sure it's float, otherwise it won't be happy. Tau is going to be tau is going to be self.temperature, and then hard is true. So in our exploration of Gumbel-Softmax, we wrote our own implementation, but our own implementation matched this one. So this is just using PyTorch's Gumbel-Softmax. It's going to take those hidden states. We have our temperature. The temperature is how we can cool or sharpen the distribution. So a high tau, like it's starting at 2, will make our distribution closer to uniform. On the other hand, a very low tau will make it closer to a 1-hot encoded vector. And hard equals true essentially just returns a 1-hot encoded vector of 1 for the most likely thing and 0 for everything else. And that's the key idea. So if we print our code vector probs, and let's just look at the first one, we're going to get something like this. We'll have all zeros except for the one thing that was selected for its index. So we have a 1 here and 0 everywhere else. And that's it. That's essentially the setup for our code vector probs, a 1-hot encoded vector identifying this is the code I want and I don't want any of these other codes. So that's it. That's our code vectors. And there's one other thing we need to do, compute perplexity. So remember, in our setup for Gumbel-Softmax, they talk about this thing called the diversity loss. And the diversity loss, it tries to promote the usage of the codebook, promote codebook utilization. Typically, if you don't encourage the use of the V entries in the G codebooks by maximizing the entropy of the average softmax distribution, yada, 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 if you don't do this, the model will end up only using a very small portion of the codebook. And we want it to actually explore the entire codebook. And so to do that, we have this diversity loss. So the way we do this is they give this form here, but they don't actually use it. They use this form right here. They compute the perplexity. So e to the power negative all of this stuff is our perplexity. And this is the form we want to calculate. This is actually pretty easy for us to do. Because again, if we do print hidden states, right? So the hidden states is this. It's this tensor of number of time steps by 320, right? That's fine. And so what we can do is this first. We're going to do hidden states is equal to hidden states. And oh, I should do hidden states dot reshape. And we're going to do the batch size times sequence length. That's fine. We're going to keep those together. We're going to pull the self.num groups dimension out and then -1. So now if we look at our hidden states.shape, we're going to have a 584 by 2 by 320. And we do this because we want to compute the perplexity, basically codebook utilization, for every codebook individually and then average it together. So we're going to do it one codebook at a time. That's the main idea. And so now that we have this, let's do one more step. Let's do hidden states. It's going to be equal to, let's see, we're going to do hidden states dot softmax axis equals -1. And let's look here. We have our, this will be the code vector soft dist, right? Distribution. So if we print our code vector soft dist, just like we have here, and let's print it for the first sample and the first codebook, so we aren't, printing out too much stuff. We got what we were looking at earlier. This is the probability distribution over our codebook. So we're this likely to use this likely to use this, ... That's it, right? That's our probability distribution over the 320 codes. But we don't have just one of them. We have a bunch of them. So if we look at everything for just the 0th codebook, right, just to keep it easy, we'll have something like this. We have the distribution for the first code, or the first embedding, distribution for the second embedding, distribution for the third embedding, ... And what we can do is compute the perplexity from this. And so let's write a method here that does this, and it'll make a little bit more sense. Def compute perplexity. we're going to pass in these probabilities, and mask is none, right? If we don't have it, but if we do, then it's there. So what we're going to do first is if mask is none, right? If mask is none, then technically we only want to compute the perplexity for the mask tokens, right? The things that we care about. We want to make sure that when we are quantizing the embeddings for those masked positions, those quantized tokens are actually using a good amount of the codebook. So we're passing the mask in, so we can grab those. We can do the marginal probs is going to be the probs. So that'll be our probabilities, but these are our probs going to be for every single time step. I'm just going to filter it out for the mask time step. So mask.flatten. Mask.flatten. So basically the idea here is that, and if we print out our, let's do it this way, we're going to do the perplexity is equal to self.compute perplexity, and we're going to be passing in the code vector soft disk. Let me just copy it in, and our mask time indices, right? And we haven't computed the perplexity yet. We'll get there in just a second, but we have all this right here, which means right now we're going to do, and this should be a mask is not none. We're going to print out our mask, and let's do the shape, and print out our probs dot shape. Looks like there is a quick bug right here. Takes 1 to 2 positional arguments. 3 were given. Let's see, what did I make a mistake here in? Oh, they see the self. There we go. All right, let's get rid of YouTube and analyze these shapes a little bit. We can see our mask is a 2 by 292 mask, right, of trues and falses, of what things were selected to be masked, what things were not selected to be masked. This 584 is just a flattened version of 2 times 292, and for each one of these tokens, we have 2 codebooks, each codebook having 320 embeddings, right? That's my mapping. And so I have logits here, or probabilities of what's the probability of picking the first code, the second code, the third code in the first codebook. And again, the probability of picking the first code, the second code, the third code in the second codebook. And so what we're doing here is I only care about computing the perplexity on my mask tokens, right? The mask tokens, because the mask tokens are the ones that I'm quantizing, that I care about quantizing. So I want to make sure that my mask tokens are utilizing the codebook in some meaningful way. And so I'm just filtering it out here, and now I get my print marginal probs.shape. It's just going to reduce down the number of codes we have just to the number of things that were actually selected to be masked, which is about half. So now we have all the masked positions. We have their 2 codes and our probability of selecting each one of those codes. And now the last part is we want to average all up. So if we look at our print marginal probs, and let's look at it for the just one of the code books. And also to make this a little bit more readable, let's do our num code vectors per group. Let's change that in our config. Let's do our num code, let's do 10 codes per group. So we have 2 groups and we have 10 codes essentially. Okay, then we can do this. So let's look at this. You'll see that we have something like this. We have 10, now let's make it even smaller. Let's do 5. 5 codes. Nice. So we see that the probability distribution of picking between the 5 codes, this is my distribution for the first quantized embedding. This is my distribution for the second quantized embedding, the third quantized embedding for that first codebook. And then I'll have the same thing for the second codebook. Now, if my codebook is being well utilized, then if I average all these probabilities together, I should get something that's close to uniform, right? Like the likelihood of using each one of these codes on average should be about 1/5, like close to 1/5. Because if it's close to 1/5, that means each code is being used equally as much. And so this is essentially what our diversity loss, or the perplexity, is going to be. Just average up our codebook probabilities for each one. Because remember, in our Gumbel-Softmax, these are the probabilities that we're going to be doing. It's going to be 18 or 19% of the time we're going to pick this code, 15% of the time this code, 24% of the time this code. But if during training it becomes, oh, like 1% of the time I use this code, 80% of the time I use this code, 3% of the time I use this code, that's not very, and if we do that, if that's the average across all of them, so like the average probability of using the first code across all our samples is 1%, average on this one is 80%, average on this one is 3%, that's not good codebook utilization. Our model is mostly using this code and nothing really else, nothing other than that. So this is all we're doing here. We're just going to compute this perplexity by doing our marginal probs. It's going to be, just add them all up. It's going to be marginal probs dot sum dim equals 0 and divide by mass dot sum, right? The number of mass positions to average it up. Otherwise, right? Otherwise, if we don't have a mass, then the marginal probs is just going to be probs dot mean. So just go ahead and just directly average it up because there is no mask or anything. And this gives us our perplexity. So if we print our marginal probs dot shape, this gives us something like this. We get a 2x5, and the values of these are even more important. We get the average probability of using this code, average probability of using this code, average probability of using this code. And that's it. That's the main idea. And we want to make sure these probabilities are as close to uniform as possible. And the way they set this up is through the perplexity, which is going to be, we're going to add up all the codes of probability times the log probability, right? And we know that when we derive this in our exploration of the paper, uniform is what maximizes perplexity. So the distribution of the highest amount of perplexity, or entropy essentially, because this is entropy, the highest amount of entropy is our uniform distribution. So let's just follow this formula. And also, once we do this for every codebook individually, and then we add it up along the code. So G is each codebook, V is all the code vectors in each codebook. So we can just repeat this. This is going to be perplexity per codebook. It's going to be torch.exp, and it was negative torch.sum. We're going to add it up together, the marginal probs times torch.log marginal probs. And of course, if we're going to do the log, just in case, we're going to add a 1e minus 7 in there. And we're going to do this along the last dimension, right? The last dimension, because we want to do it per codebook. So if we print perplexity per codebook, we'll see something like this. We have, this is my perplexity for the first codebook. This is my perplexity for the second codebook. And now I just want to add it all together. So my final perplexity is equal to perplexity per codebook dot sum, because that is again how they set it up here. They summed over all the codebooks. Good. So now we can return our perplexity, just like that. And so this is what this compute perplexity goes ahead and computes, and that's all we needed here. And we really just need this for training purposes. If we're not training, else, remember that our code vector probs here aren't really probs. They're just one-hot encoded vectors. And when I'm inferencing the model, I just need to pick the code vector that's the most likely, or the most likely code vector. So I can just do code vector probs is equal to hidden states.argmax dim equals -1, just like that. And there's really nothing interesting about this. The only reason we can do this during inference time is because, well, I'm not training. I don't need gradients. So if I don't need gradients, then I can do argmax. If I need gradients, then I need to do the Gumbel-Softmax approximation of that argmax technique. Now that we have that, we need to create a one-hot encoded vector, just like we had here. So to do that, all we need to do is just create a TensorFlow of zeros and just put a 1 at the indexes identified here by argmax as being the, whatever index is max. So we'll do argmax, and then we can do code vector probs. It's going to be torch.zeros like our hidden states, right? But just going to be a bunch of zeros. Make sure it's on the right device. Device is equal to hidden states.device. And then we will do our code vector probs at the, so torch.arange hidden states.shape 0, right? Or just batch size, but that's fine. So basically, for every sample index from 0 to 1, we have their corresponding. So we have for every sample index 0, 1, 2, 3. That's the batch index. I have the index at which from 1 to 320, for the 320 things, like the 25th thing was the max, the 4th thing was the max, the 97th thing was max, dot, dot, dot. So this is telling me which things are max, the hidden states.arg max, so I just want to fill those in. So for those things, for the, let's see here, code vector index, so code vector probs, these are going to equal to 1. So I'm just going to fill them in with 1. So now I have a 1 hot encoded vector of 0 everywhere except for the most likely hidden state, the 1 hot encoded. And then our code vector probs is going to be equal to our code vector probs.reshape, and we're going to put it in the same shape that we have up here. Batch size times sequence len by num groups by -1. So it'll be batch size by sequence len, batch size, sorry, not by, times sequence len by self.num groups, and then just -1. So that puts it in the same shape as what we have up here. And lastly, we can compute the perplexity, right? So perplexity is going to be equal to self.compute perplexity code vector probs mass time indices. So that's exactly the same. So nothing fancy here. It's just during inference mode, we get to do this. During training mode, we get to do this. And that's it. And now our code vector probs, if we print our code vector probs, we should see this. Right, so we have our 5 possible embeddings. Let's go ahead and delete this again. So we're back to the 320 that it's supposed to be. Just so it's clear. We have our probs. We have 1168 by 320. Good. And what we do now is we can reshape it again. So we're going to do code vector probs. And let's make this very clear. We have 2 codebooks, right? So for every sample, so we have here, for every sample, so let's say right here, we have basically 1 sample which has 2 codebooks. So we have 1, 2, 3, dot, 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 320, and then another 1, 2, 3, dot, 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 320, because we ended up flattening all that together, right? But really all of this is supposed to be one flat vector of 1, 2, 3, dot, 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 320, 1, 2, 3, dot, 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 320. But we don't actually have indexes. We just have a 0, 0, 1, 0, dot, 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 0, 0, 1, 0, 0, dot, dot, dot. So we'll have a 1 in my first set of 320 and a 1 in the second set of 320. Those are my indexes, right? That's all it is. And so all I'm going to do is just kind of put it back in that shape. So my code vector probs is going to be code vector probs dot reshape. We're going to make sure it's batch size times the sequence len -1, right? So we're going to reshape it back into batch time sequence by num groups times codes per group. Print code vector probs dot shape. Let's just verify that. You'll see the change immediately. It's going to go to 584 by 640. So every single thing has 640 things, and we have basically a 2 hot encoded vector, not 1 hot. We have 2 different ones in there, 1 per each set of 320, just like what I drew right here. We have 320 things. We'll have a 1 in the first 320 and a 1 for the second 320, indicating that out of the first 320, this is the one that I wanted, and out of the second 320, this is the one that I wanted. So now that we have that, we can go ahead and do the last step. Let's do a code vectors per group is going to be our code vector probs. And maybe the best way to show this actually is by the shape. So let's just print this out again. Print code vector probs dot shape. Print self dot code vectors dot shape. And this should make it clear of what's going on. So my code vector probs is this 584 by 640. My on the other hand, my code vectors themselves are 640 by 128. So let's see what's happening here. I'll just do it for one sample. Right now, let's say my code vector, let's say I have 5 codes per codebook. So let's say in the first one, I picked this one. And so this goes with codebook 1 for these 5 codes. And then let's say for the second one, I pick this one. So these 5 are for codebook 2. And I have a codebook that has 2 codebooks in it, but I just represent it as one codebook. So I can go ahead and there's 10 things here with an embedding dim. So what if I just go ahead and multiply this by this. That means I want 0 times the first code plus 1 times the second code, so that would keep this one, times 0 all the other ones. And then I'd have 0 times this one, 0 times this one, then 1 times this code, that'll keep that one, and then 0 everywhere else. So that's basically going to take this code book, 0 out all the codes I don't want, and keep the code that I want. So it's basically indexing without actually indexing, right? Nothing fancy. So let's go ahead and do that. So this is going to be, actually before we do that, there is one caveat. Notice the shapes are kind of off. We need to add an extra dimension here. So we're going to do 584 by 640 by 1 times a 1 by 640 by 128. So we're going to be broadcasting over this dimension and the last dimension in reverse, right? So we can do code vector probs dot unsqueeze minus 1. And we're multiply that by self dot code vectors. And we're going to make sure the type as self, or it's going to be code vector props. Just make sure the type is the same when we do that multiplication, and print code vectors per group dot shape, and we'll get, let's just keep that. We should get this. We'll have a 580 by 640 by 128. It's just in this 640 thing only, or in this case, if we had 10, only the selected index will be kept. So in this case, if we erase all of you and keep you, we zeroed out, basically we kept this embedding here, and we kept this embedding here. And because we multiplied by 0, the first embedding here and everything after was zeroed out, right? And then these were zeroed out. So we only kept these with 0 everywhere, and the embedding, the code vector, the original code vector in these positions. And that's it. So we have 640 by 584 time steps by 640 by 128. Now that we have that, we can wrap this up. We're first going to separate out the code book. So we have 640. We actually have 2 chunks of 320. So let's go ahead and separate those out. Code vectors is going to be equal to code vectors per group dot reshape. Again, batch size times sequence length. Self.num groups, self.num vars minus 1. So now print code vectors dot shape, right? And we're getting pretty close now to the end. We have 584, we have 2 code books of 320. Only one of these 320 things is not 0, and everything else is 0. And each of those embeddings are of length 128. Which means we can now go ahead and add them together. Because if I just go ahead, so this goes ahead, I basically took this, I split it into 2 different code books again, right? And I know that I want this code of this one and this code of this one, and everything outside of that, everything here, is just 0, right? Everything else is 0. So now I can just add everything together, because it's just adding 0 to this one vector, and that'll essentially keep the one vector that I want. And so let's go ahead and do that. So our code vectors is going to be equal to code vectors dot sum dim equals minus 2, because I want to add along my code vector dimension, so these here. So if we print my code vectors now, dot shape, I now have a 584. I have 2 codes, right, because there's 2 of them, and I have 128 embedding dim for each one of them. And now I can finally just concatenate them together. That's going to be code vectors is going to be my code vectors dot reshape batch size by sequence length by minus 1. That'll be the 128. And so now we have our code vectors dot shape, and we are done. That is our Gumbel-Softmax setup. So we now have batch size of 2, each length of 292, and we have 256 codes. And each of these codes concatenated the first code of 128 and the second code of 128 from our 2 code books. And that essentially is our concatenation operation. The reason we're concatenating is speech needs a lot of different, like when we quantize it, we want to make sure there's a large variety of things that are quantized, right? There's a lot of interesting and complex representations in speech, and we want to have enough embeddings to represent them. The problem is having large code books are very hard to optimize over. So instead, why not have 2 small code books of size 320 and then concatenate them together so you have effectively 320 squared unique different codes you can pick from. That's the main idea. So now we have our code vectors. We're going to return our code vectors, and our perplexity, right? Our perplexity. So that is finally our Gumbel-Softmax setup, right? We needed that and we have it. So we can now go ahead and do this. Okay, yeah, this sets us up for perfect. So that's our quantizer. And so that's going to be our, what we returned are our quantized codes and the perplexity, right? There we go. So if we print our quantized codes out and print our transformer outputs out, because now let's remember what we're trying to do. Let's go back to the picture. We have all of these transformer outputs, and I want to minimize the cosine similarity between my masked output and its corresponding quantized embedding. So let's just take a quick look at that to see what that looks like. And are there other stuff that we're still missing? Okay, looks like I have a mistake here. Transformer outputs dot shape is none for some reason. So let's check our Wav2Vec2 model. Was our Wav2Vec2 model? Did I miss something here? Return features to quantize was set to true. Interesting. What am I missing here? Transformer outputs dot shape. Let's see. We have our, these are my encoded outputs. So let's check our Wav2Vec2 encoder. Of course. I need to return X right here. There we go. Now it should work. A lot of code. Okay, so we have basically 2 by 292 by 256 embeddings. These are our quantized codes, and then we have our transformer output, 2 by 292 by 768. Now, of course, we can't do them if they're not the same shape, so we need to project our transformer outputs down to the 256 embed dim so we can actually compute our cosine similarity, right? So let's go ahead and do that. We're going to call this the self.project HID is nn.linear. It's going to take the config.embedding dimension. Basically, it's going to take the output of each of these and project it down to the dimension of our quantizer. So it's going to project it to config.codeVectorDim, just like that. And then self.projectQ is going to be the same thing. nn.linear is going to go from config. This will just go from codeVectorDim because it's already there to config.codeVectorDim. So just nothing too complicated, just a simple projection. And so now we can go ahead and do that. Our quantized codes are going to be projected, so we're going to do our quantized codes is going to be equal to, and actually, yeah, let's do self.projectQ, and we're going to project it with project our quantized codes, and then we're going to have our transformer VQ. We're going to project our transformer output to this vector quantized dimension. It'll be the self.project HID transformer output. Print quantized codes.shape, transformer VQ.shape. Let's verify that they're the same shape, and if they are, we're good to go. And so yes, we can see both of them are at 256 embed dim. And so now that we have that, it's time to compute our loss. So loss is none. Our diversity loss is also none. And then our contrastive loss, the one we mostly care about, but they're all important, is also none. And we're going to do if sampled negative indices is not none, right? If it's not none, then, right, that means we actually have, sampled negative indices. Let's go ahead and remind ourselves again. Sampled negative indices. What was it? It was for every single sample if it was selected to be masked, so it's kind of hard to see here, but let's see. Let's do, will that work? Let's see if that indexing breaks something. Okay, so we can see for this specific mask time step, these are the negative indexes I picked. For this time step, these are the negatives I picked. For this time step, these are the negatives I picked. So the first thing I need to do is collect all the negatives, right? So I need to go into my quantized embeddings, and for this sample, grab the 10th one, the 111th one, the 99th one, the 203rd one, For this sample, the 274th quantized embedding, the 222nd quantized embedding, 256th quantized embedding, ... So we just need to repeat this, right, for all of them. So that's relatively straightforward. We just need to collect those quantized codes. So we're going to do batch size by sequence length by VQ size, so that's what this is. It's going to be the quantized codes dot shape. And then we're also going to have num negatives is going to be sampled negative indices dot shape. In our case, this num negative should just be 100, right? So now that we have all our quantized codes and the indexes of the negative samples, we actually need to grab those quantized codes, right? So again, remember, the quantized codes is going to be batched by sequence by VQDim, and the sample negatives is batched by sequence by num negatives. So all we need to do is for each negative in our sampled negative indices, there's also a mask token that we want to compute that contrastive loss on. So we need to grab its quantized latent, which we did, right? So we implemented when we did the utils dot, if you remember, the reason we adjusted down here for our batch dimension for the index is because everything's already flattened and kind of ready to go. So let's go ahead and start setting this up. So our negative quantized codes is going to be the quantized codes dot reshape, right? Let's do reshape. It's going to be -1 VQ size. So if we print our negative quantized codes dot shape, you'll see that we have has no, oh, this one, my bad. Try that again. You'll notice, right, that's what I have, 584 by 256. I have 584 time steps, but the first 242, or 282, whatever it is, come from the first sample. And then the second half of it comes from the second sample. It's just flattened, right? We flattened it all together. And again, this, just to remind, be very specific, we had embeddings from one thing, we had embeddings from another thing, and we just flattened it all together to become one long thing, where I know this part goes with the first sample, this part goes with the second sample. Thus, that's why I did the offsetting, right? So my indexing is 0, 1, 2. That means it's 0, 1, 2 here, 0, 1, 2 here. But then this is technically 1, 2, 3. So that's why we added +3 to here. So actually not 1, 2, 3, sorry. This should be 2, 3, 4, 5. That's why when I added 3, this became 3, 4, 5. That's why we offset the indexes, just so we can flatten and have everything aligned and be easy. So that goes ahead and does that. But let's also look at our sampled negative indices. Oops. Sampled negative indices dot shape. And this looks like this, right? 2 by 292 by 100. So let's go ahead and flatten this as well, right? 2 by 292 by 100. Let's go ahead and flatten it like so. Dot flatten. And this ends up being a very long list of just indexes that refer to these time steps right here, right? These are indexes that refer to 0 to 583, right? These indexes here. So if we print out u, just so we can be as clear as possible, we have these indexes here that refer to 0 to 583, whatever right here. And that's what we're going to be using, right? We need to use that to essentially index it. And we can do that by doing sample negative indices dot flatten. And this is going to grab essentially everything we care about. So if we do print negative quantized codes dot shape, it's going to go and grab that. So basically, let's draw it out just to make it clear. We have a sequence of inputs, and all we're doing is grabbing. We have essentially some indexes, right? So let's say 2's, let's make it clear, 2, 3, 1, 5. Let's say that was our set of indexes. So this is going to go in when I'm indexing it like this, right? These sampled negative indices. We don't have just one of them. We have a bunch of them. There was batch by sequence, right? So we can go ahead. We'll have another set right here. 1, 7, or not 7, 7 isn't in our thing, 1, 3, 1, 2, 2, 1, 4, 3, dot, 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 right? We have all of these. We go ahead and flatten all of them. So it'll give me a list of 2, 3, 1, 5, 1, 3, 1, 2, 2, 1, 4, 3, right? I just went ahead and flattened them. And then I go into here and I index them. So that means I'm going to first grab the second embedding. Then I'm going to grab the third embedding. Then I'm going to grab the first embedding. Then I'm going to grab the fifth embedding. Then I'm going to grab another one of the first embeddings. Then I'm going to grab the third embedding. Then I'm going to grab another one of the first embeddings. And we're just going to basically line them all up. So we're going to essentially have like an embedding for each one of these that we copy over, index over, from all of our possible indexes. So this will come from 2, right? The second one. This will come from the third one. This will come from the first one. This will come from the fifth one. Dot, dot, dot. And we just do this for all of them. So we'll end up just copying all of the corresponding indexes of the embeddings that we care about. And this is, again, why we offset everything, right? We offset it so indexes 3, 4, and 5 make sense from like our original set of indexes. Because, again, it goes 0, 1, 2, 0, 1, 2. But then it wouldn't work out this way. We have to do 0, 1, 2, 3, 4, 5. And that's why we offset everything so we can just index everything nicely like this. A little bit complicated, but not too bad once you wrap your mind around it. So that goes ahead and grabs my negative quantized codes. But of course, we don't want it in the shape, so we're going to do negative quantized codes is going to be equal to negative quantized codes dot reshape. We're going to put in the shape of batch size by our sequence length, by our num negatives, by our VQ size. That's going to kind of just put it all together. We print negative quantized codes dot shape. This puts it in the shape that makes more sense. For every sample, for every time step, we have 100 different negatives, and each negative is 256 things. And we essentially index those negatives. Now, this is the less convenient way to have it in. So I'm going to put the shape, I'm going to change the shape a little bit. I'm going to put the negatives at the beginning. So I'm going to shape it to 2, 0, 1, 3, right? So we're going to do that. Dot permute 2, 0, 1, 3. Just put the dimension of the num negatives first. So there we go. We have 100 negatives, and we have 2 samples, 2 batch size of 2, 292, 256. Good. Now that we have that, it's time to compute our cosine similarity. This is actually pretty straightforward. So we can do let's write a method, def compute cosine similarity. And this is going to take our target features. It's going to take our negative features, our predicted features, and the temperature, right? So temperature, they use in the paper a default temperature of 0.1 for computing this cosine similarity. So what are we doing here exactly? What we want to do is set up our data kind of like this. For every sample, so we have some z time step, let's say 3, z time step 3. I know my correct answer is going to be Q3. But I've also sampled some negatives, some random negatives. That's like Q5, Q7, Q1, dot, dot, dot. So we have 100 distractors or negatives here, and we have my correct answer right here. And so what I want to first do is my target features are my correct answers. So let's start with that. Our target features, let's go ahead and compute the cosine similarity. So that's going to be the cosine sim. It's going to be self.compute cosine similarity. Target features is going to be our quantized codes, right? These are my correct quantized codes. My negative features is going to be the negative quantized codes. These are the ones that I've randomly sampled as my negatives. I have my predicted features. It's going to be the transformer VQ, right? These are my transformer outputs. And then I have my temperature is going to be self.config.contrastive logits temperature, right? There we go. So let's look at my data. We have print our, let's see, what's the easiest way to show this? We can do maybe target features dot shape. Let's look at this first. Let's see, multiple things for, we have to do self So we have 2 by 292 by 256. These are my correct quantized embeddings that, just line up with my data. And then I have print negative features.shape, and I have print our, which one is it? I called it predicted features. These are the transformer outputs.shape. So let's just look at all of them. So my transformer outputted 2 by 290, 2 by 256. And of course, I only want to compute the loss on the mass tokens, but for now, ignore that. We have, this is my output. I know for each one of these embeddings of 256, these are my correct answers. These are my 256 actual correct embeddings. But I have 100 additional distractor embeddings that I'm going to be using for that contrastive loss. And so this is why we're going to end up concatenating together my correct answer with my incorrect answers and then compute the cosine similarity and do it that way. So what we're going to do is target features is equal to target features dot unsqueeze 0. Let's just add an extra dimension here at the beginning, a 1 essentially. So it'll be 1 by 2 by 292 by 256, and then I have 100 by 2 by 292 by 256. So we can do targets is equal to torch dot cat target features and our negative features dim equals 0. And if we print out our targets dot shape, we'll have 101. We'll have 101 things, right? In the same way, like right here, we'll have 1 plus num negatives. So you have 100 negatives plus 1. We'll have 101 things where the first index is the correct answer and everything else is the incorrect answer. So we have 101 things. And this is why in the paper, again, they mention k plus, let's see, that's not helpful. It's, where is it? I believe they say it somewhere around here. Here we go. In a set of k plus 1 quantized representations, which includes qt, the correct answer, and the k distractors. Right? So there we go. 101, where k is 100, so 101. All right, so that's our targets. And now what we want to do is compute the cosine similarity between the predicted features, print, so predicted features.shape, targets.shape. Let's just be clear. We have 2 by 292 by 256 outputs from our neural network. And we have 101 possibilities for targets. So I want to compute the cosine similarity between this, every single one of these, and every single one of these. And so we can use torch.cosine to do this pretty easily. We can do cosine sim. It's going to be torch.cosine similarity. We're going to do predicted features and our targets, and it'll be dim equals -1, right? We want to compute the cosine similarity along the embeddings, this last dimension here. So it's going to compute the cosine similarity between this and every single one of these and get our pairwise relationships. And that's the equivalent of computing the cosine similarity between this and this, then this and this, this and this, this and this. Just do it for each one of them, and it's going to produce some number, right? We'll have, essentially we'll have some similarity 1, similarity 2, similarity 3, dot, 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 up to similarity 101 for the 101 things we have. And we want to maximize, or I guess we want to minimize, we want these to be the most similar, so maximize their similarity, and we want it to be the least similar to these. So there we go. That's our cosine similarity. And of course, we need to scale it by the temperature as per the paper. So cosine sim is equal to cosine sim divided by temperature, and we can return our cosine sim. What this looks like is, if we look at our print cosine sim.shape, we're going to have the cosine similarity between all those pairwise relationships. It'll be a 101 by 2, batch size of 2, by 292. So for every single time step, we have the cosine similarity between the input and all of the possible outputs. And that's basically it. That computes our cosine similarity. Now, there are a couple of little practical things that we need to keep in mind. The entire point of cosine similarity is if we want to minimize the difference between Z3 and Q3 and maximize it to everything else, right? We want the cosine similarity to be quite similar between these. Now, what if at the beginning of training, of course, our quantizer may not be working so well, right? We haven't really explored the quantizer. And it could end up that Q3 and Q5 and Q7, like a lot of our codes end up being identical to each other. The problem with that is if Q3, Q5, Q7, and whatever, if they all are the same, because during the quantization stage, our codebook utilization is very low, and our neural network is mapping all of our embeddings to the same Q, then when we compute cosine similarity, that doesn't work anymore because Z3 will be, sure, we're computing the cosine somewhere between Z3 and Q3, Z3 and Q5, Z3 and Q7, dot, dot, dot. But if all the Qs are the same, then all of these similarity values are going to be the same. And if all the similarity values are the same, the model will not be able to learn anything from that. So one thing we need to do, this is mostly important for stability at the beginning of training, is to make sure that if we have any quantized codes that's equal to our negative quantized codes, we need to go ahead and just fix that. So we're going to do neg equals pos mask. This is going to be if our quantized codes, so our originally quantized codes, if it's equal to any of our negative quantized codes, dot all, dim equals -1, then we want to replace those. So again, the idea is if Q3, my quantized code, is equal to Q5, if these two things are equal, let's use a different color. If these two things are equal to each other, I just don't want to include this in my contrastive computation because it doesn't make any sense. And if this is equal to multiple things, right, let's say it's equal to the first two things, then I don't want to include either of these in the contrastive computation. So my neg equals pos mask is essentially doing exactly that. It's checking, is my quantized code equal to any of my negatives? If it is equal to any of my negatives, go ahead and replace them, right? That's the main idea. So we're going to do if neg equals pos mask dot any. So if there were any cases of them being the same, we're going to do cosine sim from 1 to the n, because remember the first index is our actual data, right? Like it's our actual correct answer. We don't want to change that. But everything else we can replace. Neg equals pos mask is float negative int. We're going to fill it with negative infinity because when we do cross entropy in a bit, it'll take us off max and negative infinity will become 0 and then we don't have to worry about it anymore. So we're going to set them to negative infinity as unsimilar as possible, so it's something we don't have to worry about. So finally, we can now compute our contrastive loss. So print our cosine sim. We should actually see some cases of our neg equals pos mask being true, or a lot of them, see lots of them at the very beginning of training, will always be negative infinity because there's just so many because the model hasn't learned anything yet, hasn't been trained. All the weight layers are just basically projecting to the exact same embedding. So just at the very beginning of training, this stability is important to make sure that we're not including extra stuff. So we need to compute our cosine sim. So cosine sim is going to be cosine sim. Let's do permute, and we're going to do 1, 2, 0. So we're basically just transposing a couple dimensions around. And now if we look at our cosine sim dot shape, we have 2 by 292 by 101. And let's just also reshape it. Dot reshape batch size times sequence length by num negatives plus 1, right? That's, or we get a -1, that's fine. Num negatives plus 1, 101. So we have 584 by 101. And here's the key idea. We have 584 by 101. But I know, remember, how do we do classification normally? In classification, you have an index saying, if you have like an image, it'll say like, oh, the image is a dog or a cat or an apple or a bridge, and we have some index that references, right? Like 7. If let's say we're doing dogs, cats, and cars, right? Dog, cat, car. Then it's 0, 1, 2, and the neural network will predict: is it this? Is it this? Is it this? What is the index? That's our label. But we know what our label is. We know for sure, because that's how we set it up, the very first item in our 101 things is the correct answer. Correct. That means the correct answer index is just 0. So when we use cross entropy, which is the easy way of just doing this, go ahead and just set the label as a bunch of zeros. So let's do this. We can do our labels. We're first going to create as ones. Torch.ones, and it's going to be len cosine sim. So print labels. So we're just creating a tensor of ones here as our labels. Doesn't make sense yet, but that's fine. Now we only want to compute the loss on our the mass tokens. Make sure the device is equal to cosine sim dot device. There we go. So we're going to multiply this by -100. So basically everything here will be set to -100, right? So this means ignore loss. We don't compute loss on these things. And then what we're going to do is our labels, and only for the mask time indices dot flatten, only for those indexes are we going to set it equal to 0. So what this is saying is that, oh, I need to print it just so it's clear. Print labels. We have -100 for all the unmasked positions, and for the positions that are masked, the correct answer is 0 because it's the 0th index, right? This first column, that is the correct answer for each one of them, right? So it's always this first value that's the correct answer, and so that's why we're going to set them to 0. And this is essentially going to act as our label for the cross entropy loss. We don't necessarily have to do cross entropy. We could have done it other ways. Cross entropy is just the easy way of doing it. So contrastive loss is f dot cross entropy, cosine sim, labels, and reduction equals sum. So this is one thing. Our loss values are actually going to be pretty large because we're going to add them up. But because we want to train on multiple GPUs, I don't know ahead of time how many quantized codes, how many mask tokens I have, right? So like one GPU might have 5 mask tokens, another one might have 25 mask tokens, just depending on it's random. So I'm going to just add everything together for now, and I'll divide by the number of mask tokens during training time. So we'll see that when we actually get there. For now, we're just going to average them up. So and last part, our diversity loss, we're pretty close. We computed perplexity, which is actually just this part right here. We're going to do GV minus perplexity divided by perplexity. That way it becomes a minimization rather than a maximization. And so that's fine. We can go ahead and do that. So it's going to be GV is going to be self dot config dot num code vector groups times self dot config dot num code vectors per group, right? Just like that. And so our diversity loss is going to be equal to GV minus perplexity divided by, and let's throw another parenthesis around it, divided by GV. That's the loss they gave. And the reason, again, we're doing this is mostly because we want to make sure we're minimizing, right? So to minimize this function, GV and GV are constant, so we have to increase this value here for GV minus this to decrease. And to increase this is to maximize our perplexity, right? So it essentially sets our problem up as a maximum problem. Now, one other thing is, like I mentioned, we did a reduction equals sum here because we're going to divide by the number of mask time steps in the future, right? We haven't done it yet. We'll do that in training, but we're going to add up how many mask time steps we have and then divide it after the fact, which means we need to make sure we scale this up by mask time indices.sum right now, because we're going to divide by this value a little bit later, just so we don't mess the scaling up. We're going to include that here. It'll disappear during training anyway, so it's fine. And so then our loss will be finally the contrastive loss plus self.config.diversity loss weight times diversity loss. And so this is, again, if you have multiple loss functions, we have to kind of weigh them against each other. And I think we use a 0.1, right? So 0.1 is our diversity loss weight. So that is our final loss. And now we can finally return, and I'll just copy this in because I'm a little tired of typing all this. There we go. Return that Wav2Vec2 for pre-training. We have our loss. We have our transformer outputs, quantized codes, perplexity, contrastive loss, diversity loss. Really all we care about is this final loss value, but we'll use the rest for logging purposes. And that is essentially a full implementation of the Wav2Vec2 pre-training setup, right? So we kind of put it all together. There are little nuances because when it comes to training, we just have to make sure things like train in some stable manner. The main thing that matters really is this, especially at the beginning of training, making sure to set up your neg equals pos mask. But now that we have that, looks like we have a small issue here. Found float because we need to set u when I create the torch.ones dtype equals torch.long tensor. That's what cross entropy expects. Am I missing a device? There we go. Now it should work. Good. So we got some loss value, and we'll be, as we train, it'll do stuff. All right. So that basically sets up all of that. Now for our CTC model, it will be almost identical. So which is why I might not even bother Yeah, I don't really even need to bother typing this. We can just kind of go over the code because this is the less interesting part. And there's just a couple extra things that I've put in here. So the Wav2Vec2 CTC, it's exactly the same thing. What we're going to do first is load a backbone. And this is the extras part. I go ahead and load in my config. I have some options here. If I want to use a pre-trained backbone, a pre-trained Hugging Face backbone, so this is grabbing the Wav2Vec from Hugging Face, or a completely randomized backbone. By default, we'll use pre-trained. If we're using a pre-trained backbone, then go ahead and just load the Wav2Vec2, my own Wav2Vec2 model, and load those keys in, and we're done. And there's just a little bit of a, I have to change I just have to clean the names of the weights and keys up a little bit because that's just how it's saved, so we can just remove some of this extra stuff. And we can load that. Otherwise, we can load the Hugging Face Wav2Vec2 model in the same way, right? But the interface is identical. I try to make them as similar as possible so nothing really has to change. So that's just me loading the backbone. And then for CTC, what we're going to do is we'll have a dropout layer and then a head, right? And the head's going to predict for every single time step all the possible characters, right? The vocab size that it could be. And so during inference time or during training time, typically what we do is we freeze that Wav2Vec2 backbone, the convolutions. There's no need to train that anymore. We just train the actual transformer layers themselves. So we'll freeze the convolutions. That's what this is. If we're doing in Wav2Vec, Hugging Face already has a method to do that for you. Otherwise, I will just do it myself, right? I'll loop through my feature extractor and shut them off. Lastly, for our forward function, this forward function should look almost identical to the one that we did for our DeepSpeech 2 architecture. So what we're going to do is pass in our input values, attention masks, and the corresponding labels, right, the targets, and we can grab our hidden states. If we're using the Hugging Face, then this is how we grab the hidden states. If we're doing it in our way, then this is how we can grab the hidden states from our Wav2Vec encoder, right? So again, this is just using all this extra pre-training stuff, like the Gumbel-Softmax and all that. All this disappears. We don't really care about that anymore. All we care about is our standard Wav2Vec2 model, right, which outputs transformer embeddings, and in that case, we'll do return features to quantize as false, because we don't really need these anymore, because there's no quantization happening. Once we've done that, we can go ahead, do dropout, language model head, and then computer loss like normal. We can go ahead and do if labels is not none, if attention mask is not none, go ahead and produce the attention, attend to everything, that's fine. We can get our input length by computing the encoded length. So this will tell our CTC loss function what is the length of the inputs. It also needs to know the length of the targets. We can compute that as well. We need to provide it the flattened targets, the log probs, the blank token. In this case, in the Wav2Vec tokenizer, we just use 0 as our blank token, so we'll just use that here. And then we have a reduction, right? We want to average up our losses and 0 infinity. So there's nothing fancy happening here. We just compute our log softmax of the logits and then provide the log softmax to our standard CTC loss. Nothing fancy. This is almost identical to the one we did in that DeepSpeech 2 architecture and the least interesting part. So we just have that here. We won't even write a training script for this. We'll just use the Hugging Face like trainer to train this model and it'll be fine. All right, let's go ahead and now implement the pre-training loop for the Wav2Vec2 architecture. So I've already gone ahead and just copied in a bunch of stuff here. I'm importing my Wav2Vec config that we wrote, the Wav2Vec2 for pre-training model that we wrote, as well as our collate function for pre-training and the LibriSpeech dataset, right? So we have everything, and then we have accelerate, getting our scheduler, all that, so standard stuff. I've copy pasted in this giant config file in, so this lets me control everything about training, and I will be running it through this bash file right here, which basically has all of the same things. So yeah, nothing crazy. I've gone ahead and just limited the train split to just be that, so it's just easy to just make sure everything is working accordingly. And everything here is set to the paper's definition. So they use like a polynomial scheduler with these atom values, this learning rate, that sort of stuff. So let's just go ahead and get started with our setup. Let's, okay. Actually, you know what? There is one thing that we forgot to do. In our Gumbel vector quantizer, we set the temperature to 2. We want to make sure that we actually decay this temperature as we're going. So we're going to see how we do that as well. So we can actually do that manually later. That's fine. So yeah, let's go ahead and get started and make sure everything is open. All right. So our training setup will be pretty much like always. Args is going to be parse args. Okay. If args dot seed is not none. Then we can do set seed from Hugging Face to set seed args.seed, right? Just go ahead and set the seed. And we're going to need our standard, and actually let's just go ahead and copy paste a lot of stuff. This is not as interesting to anyone. Let's copy all of you in here. There we go. So this is going to go ahead and set up our accelerator. If we want logging with weights and biases, init that tracker, and here's our config with all of that information from our argparse. All right, now that we have all of that, there are a couple things we're going to need to do. Let's start with this, and let's just put it at the top so it's clear. Helper functions. There we go. So there's a couple helper functions we're going to need to write. The first one is going to be def multiply gradients. We're going to have a compute gradient norm, and then compute batch dimension. There we go. Or not batch dimension, but batch duration. There we go. All right, so step one, multiply gradient. So again, if you remember, in our model, when we compute our loss, like we do right over here, we do reduction to sum. And so we essentially add all our gradients together. So when we do dot backward, it's going to be way too large. We need to scale it down by the number of items that were in our loss, right? The problem is we can't do that easily because every time we do a forward pass, the number of mass things can change because how many mass tokens are selected to be mass change every single time. So what we're going to do is just add up all the losses together and then divide by the number of mass things across all the GPUs, just to have the most accurate gradients. Now, when I divide the gradients, I need the method that will actually divide the gradients by some constant. So let's go ahead and add that in. So what this is going to be is essentially for param, and what we're going to pass in is some params constant. For param in params, we're going to do if param.grad is not none. So if it has gradients, go ahead and do param.grad.data.mul in place constant. Right, so we're going to go ahead and just update the gradients by manually multiplying them by some constant. And the constant's going to be some decimal value, less than 1. So there we go. We also want to compute our gradient norms. This is more to see how the model's going. So when we're training, param scale equals 1. When we're training our model, we want to make sure that all the different layers of the model are getting good gradients. If our gradients are not good, that means something is going wrong. And in the pre-training example from Hugging Face, they expect the gradients to be something between 0.5 and 2. If it's too large, the training is unstable. If it's too small, then it's going to be like it's not learning enough or something else is unstable. So we're just going to compute that here. The other thing is you see the scale here. When we train in mixed precision mode, your gradients are automatically scaled by the system, in this case Accelerate. So the scale is by default 1 because no adjustment is needed to the gradients, but if it's adjusting it, we're going to make sure we include those adjustments in our gradient computation here as well. So total norm, we're going to make it 0, and before p in params, if p.grad is not none, so for every parameter that has gradients, we're going to do param norm is going to be p.grad.detach, go ahead and detach it, .data, we're going to divide it by its scale, right, just in case it's 1, it doesn't matter, but that's fine. And we're going to go ahead and norm it, right, compute the norm. And total norm plus equals param, total norm, it'll be param norm.item squared. Right, so go ahead and add all the square norms to our total norm, and then our total norm will just be the square root, right? Standard square root of that, 0.5, return total norm. No problem there. The last thing we'd be interested in is what is our batch duration? So how many seconds of audio am I processing in every single batch? In the original Wav2Vec, I believe they do like 1.5 hours or something like that. Huge batches of 1.5 hours of audio in each pass. I can't match that myself, but that's fine. We don't need to worry about it too much. Sampling rate, Let's just compute it up. So remember, our attention mask is just a 0, 1 vector, or a 0, 1 matrix, where it's 1 for all the samples that are, and this is the attention mask on the original audio, not the sub-attention mask. It's 1 for all the samples of audio that are real, and then 0 for all the samples of audio that were padded on. So as long as we just add it together, so our total duration seconds, it's going to be torch.sum, attention mask. This will tell me how many samples have, and we'll do the sum, dot axis equals -1. This is going to tell me how many samples are actual samples of audio, and tell me how many samples there are in that audio file. And then we can divide by the sampling rate, which is samples per second. So this gives me the total duration in seconds per sample. And then we can do our total duration. Let's see here. We can, and then once we've done that, we can do torch.sum and add it all together. Right? Just add it all together. There we go. So this will give me the total number of seconds in my audio, in my batch of audios. And then we'll do total durations divided by 3,600, because it's 3,600 seconds in an hour. So total duration, this will be hours, and we can return total duration hours. So these are just a couple of helper functions that we're going to need for training purposes, and we'll see where they're used in just a bit. So we have our accelerator set up, we have our config, just me filling in our big Wav2Vec2 config with all the stuff that matters. And so now that we have that, let's go ahead and start writing the rest of it. Our model is going to be the Wav2Vec2 for pre-training config. The model parameters is going to be filter. Let's just go ahead and grab all the parameters that requires grad, model.parameters. And then we'll do params is equal to sum, and we can just add it all quickly together. np.prod, p.size, for p in model parameters. So I'm going to loop through, and I'm going to add together how many parameters I have, so I can print out, and I can do accelerator.print, number of parameters is going to be params, right? So it's how many trainable parameters we have in this. And now let's go ahead and set up our train split, test split. All of this stuff is basically the same as always, so I can go ahead and copy these things in. Right, so we're going to prepare datasets. This is that same LibriSpeech dataset we wrote with the path to the audios and what splits we want to do and what transcript, everything. Right, so everything is in here, so we're good to go. And we're going to return transcript as false because we don't need the transcript for the purposes of training, for pre-training. And then data collator is going to be our Wav2Vec2 collate function for pre-training. This will also get that config. And we can do our mini batch size. So this is important. Our mini batch size, if we're doing grained accumulation, then we'll do args.per GPU batch size, which is something I set. How many samples do I want per GPU? Divided by args.gradient accumulation steps, right? So I'm going to split my batch size up into these different accumulation steps. So then every batch will be the mini batch size, and we'll accumulate them up to the overall batch size that I want. So my train data loader will be my standard data loader. We'll have our train set. Batch size is going to be the mini batch size. Our shuffle. We can shuffle. We can also not shuffle. It doesn't really matter because the data is pretty non-homogeneous anyway. Num workers is 8. Collate function is our data collator that we just defined. And then, yeah, that's actually it. So there we go. And this should be train set. And our test loader will be identical. So we'll call this the eval data loader. This will be on the test set. Everything else is identical. So we're good to go. Our optimizer, standard optimizer, is equal to torch.optim.atomw model.parameters. They actually set the, okay, so we have the learning rate is args.learning rate. They set the betas to default, different from default. So it'll be args.atom beta 1, args.atom beta 2. And then EPS, right, will be args.atom epsilon. There we go, that's our optimizer. Of course we need a scheduler, right? They use the polynomial scheduler, so we'll do scheduler, it will be get scheduler, and we're gonna give it the name equals args.lr scheduler type. This get scheduler is just a method that Hugging Face has that makes it very easy to grab schedulers. Optimizer equals optimizer num warm-up steps, or num warm-up steps. If we want to have a warm-up part of our scheduler, then it's going to be args.num warm-up steps, and then num training steps is args.num training steps, just like that. And so now that we have everything, we can go ahead and prepare everything. Model, optimizer, train data loader, eval data loader is accelerator.prepare. And we'll do again model, optimizer, train data loader, eval data loader. And we are good to go. And of course, we also want to do accelerator.register for checkpointing our scheduler, because we want to make sure we checkpoint that as well as we're training. Now, just like always, we want to be able to resume from checkpoint. So if args.resume from checkpoint is not none, so if we pass in a checkpoint that we want to resume from, then our path to checkpoint is going to be the os.path.join, and we're going to do the path to experiment and the args.resume from checkpoint, right? That's going to be the path. I like doing my checkpoint names like checkpoint like number, like whatever checkpoint iteration we're on. So we'll just do exactly that with accelerator.main process first, accelerator.load state, and we'll do path to checkpoint. This is going to go ahead and load the checkpoint into our model. So we're ready to go to pick up from where we left off. And then our completed steps, how many steps have we already trained for? It'll be int args.resume from checkpoint, which is again that it'll be that string of checkpoint underscore number. So we can do dot split on the underscore, grab the last thing and convert it to an integer, and that will be it. And we can do accelerator.print resuming from checkpoint completed steps, right? Or not checkpoint, but iteration. And so that's basically it. Otherwise, if we're not resuming from checkpoint, then completed steps is just 0. Now it is time to actually train our model, train model. So let's start this. We're going to do train equals true. Progress bar is going to be TQDM range completed steps to args.num training steps, right? So however many steps we started from, 0 at the beginning or however many, to however many we actually want. And we'll just do a quick disable equals accelerator dot, and it'll be disable not accelerator dot is main process. We don't, when we're training on multiple GPUs, no need to print out the progress bar multiple times. And so now we can do while train. And so there's a couple things, because we have gradient accumulation, we need to keep track of a couple of things we need for accumulation. First, accumulated steps is 0. So how many steps of accumulation have we done so far? Accumulated hours per batch is 0. So if we want a batch size of 64, but we can only do them in chunks of 32, then I need to accumulate up the total amount of hours in each one of those batches. So there we go. And then accumulated percent masked is also 0, right? So there we go. That's going to tell me what percentage I actually mask things out, so I can recompute stuff. Let's go ahead and start. So for batch, in train data loader, we're going to do num losses is going to be batch, and this is going to be the masked time indices dot sum. Remember again, this is a 0, 1 vector or matrix of ones of things that are being masked and 0 for things that are not masked. So if I sum it together, that tells me how many losses I'll be computing in this specific batch. And so there you go. That's basically our scaling factor that I keep mentioning. That's why we needed to, in our model, for example, when we computed our loss, we went ahead and multiplied by the sum of the mask time indices here to scale up the diversity loss, because I'm about to divide it by a constant when I scale my gradients. And so I need to, and that's exactly the same thing that will be scaling. So there we go. Our hours of audio is just going to be the compute batch duration. It'll be the batch. We're going to pass it the attention mask, and it'll be args.sampling rate, which will be 16,000 by default. And we can store in here accumulated hours per batch plus equals hours of audio in case we're doing multiple accumulations. Our percent masked, what percentage of the data was masked, will be the num losses divided by batch sub attention mask dot sum. So there we go. So again, we want to make sure we scale it by the actual how many non-masked positions we have. So we have our sub attention mask, 1 for the values that actually is actual data, 0 for the values that's just padding, and I go ahead and scale my num losses, the number of things that are being selected from masked, by that, so we get the proportion, because we don't want to include padding values in computing this proportion. That doesn't make any sense. And so now we can do accumulated percent masked plus equals percent masked. Now let's go ahead and do our, and of course, percent masked divided by args.gradient accumulation steps, right? Because it's a percentage, right? So I'm going to just add up the percentage mass over and over again and then divide by gradient accumulation steps, or just add it already scaled by accumulation steps. So if we have 2 steps, then it'll be percent over 2 plus percent over 2. Or I just added the percent plus percent divided by 2 afterwards. Doesn't matter. You can do it however you want. So now our batch, we want to make sure everything's on the GPU. So KV, it's a dictionary, .2, accelerator dot device for KV in batch dot items, right? Just go ahead and loop through them, make sure everything's pushed to the GPU, and then outputs is going to be model, and we're going to be passing in this batch, right? Pass in the batch. And the loss is going to be outputs, the loss value, and again we'll scale it by args.gradient accumulation steps, right? Because we want to average it up across all the steps. And then accelerator dot backward loss. That's going to go ahead and compute those gradients. Now, a couple of things. We need to scale these gradients. I just computed backwards, but I need to scale these gradients by the number of GPUs and the number of losses. So let's go ahead and do that. We're going to do if accelerator, and this is if we're training on multiple GPUs, dot state dot num processes greater than 1. So if we have more than 1 GPU, which is standard for big models like this, then we're going to do num losses is going to be accelerator dot gather for metrics, num losses. So remember, num losses is just a value. It's just some value that we've computed. But of course, if you're training on 4 different GPUs, we're going to have num losses on the first GPU, second GPU, third GPU, fourth GPU. So I'm going to gather them together, and this essentially just creates a list of num losses for the first GPU, num losses for the second GPU, ... We'll do it for each one of them. And so I just want to sum all of them together. That gives me the overall num losses across all the GPUs. And then our gradient multiplier is just going to be accelerator dot state dot num processes divided by num losses. So the reason we're going to multiply by the number of GPUs and divide by the num losses, well, we have to divide by num losses anyway. But in accelerate, by default, they're going to already divide by the number of processes. So I want to make sure that I basically want to not want to undo something and basically do it twice. So we're just going to multiply it by here. So when it does it, it'll all be equivalent. And so we are now good to go. We can now do multiply gradients, model.module.parameters. Remember in accelerate, when you're training on multiple GPUs, the model is hidden. All the stuff in your model is hidden under this like extra module wrapper. It basically wraps your thing in a DDP thing. So we have to access it with module, gradient, multiplier. So yeah, that's basically it. We are going to compute this gradient multiplier, which is just going to take the number of processes we're training by, divide by the total number of losses, and then scale all our gradients down by that method. And again, we wrote that method up here to just loop through all the parameters and multiply all of our gradients by that constant. And this will just scale it down exactly by the number of losses we have and make it consistent across all the GPUs. Now that we have that, we can do else, just multiply gradients, model.parameters. If we only have one GPU, it's just model.parameters. It'll just be 1 divided by num losses because it's just one GPU. Right, so there we go. Nice. So now that we have all of that, we have completed one step. So we can do accumulate steps plus equals 1. And this should be accumulated. Let's just call it accumulate. That makes more sense. Accumulate steps. So we've completed one step of accumulation. Now, if accumulate steps percent args.gradient accumulation steps, right? So if we want to accumulate 2 steps, then basically every 2 forward passes, we're going to trigger this, 0. Then we can do if has adder, and this is kind of just extra stuff that most people don't care about, but it's just good for logging. Has adder accelerator scalar. So if our accelerator has this scalar attribute and accelerator.scalar is not none, so if the accelerator is scaling, this will be true for any kind of mixed precision mode. And we want to make sure it's not none, because if it doesn't need to scale, then it just stays as none. Then we'll do our scale is going to be accelerator.scale.item. Right? So this is the automatic scalar that accelerator is doing for mixed precision purposes. So we can grab that scaling value to make sure we are also logging our final gradient norms in the correct way. Otherwise, we can just do scale is just 1, right? Scale is 1. So if accelerator.state.num processes is greater than 1, then we're going to do our grad norm is going to be compute gradient norm model.module again .parameters. So you have to reach into the basically have to reach into the DDP wrapper with the scale. Else grad norm is just going to be compute gradient norm model.parameters like normal scale. So again, this is going to go ahead, loop through all of the gradients of my parameters and compute what's my total norm of the gradients. And it gives you an idea of the gradient health, right? How things are going. Okay, good. So now that we've completed all of that, it's time to update our model. Optimizer.step, optimizer.0grad, and then scheduler.step, right? We can update our scheduler as well here. And now it's time to update our Gumbel temperature. So something that I may have failed to mention is that when we train our model, when we train our neural network, we have our Wav2Vec model, the Gumbel-Softmax Quantizer, again, has this temperature parameter. Where did it go? We have our temperature, right? And temperature controls the kind of the sharpness or the uniformness of our distribution. If you have a high temperature, our logits, or basically the probability over the codes, will be more or less uniform. If you have a low temperature, it'll be closer to 1 hot, where one of the codes is picked. At the beginning of training, it makes sense to have it be a little bit more smooth, a little bit more uniform, because your model doesn't know which code to pick, right? It has no idea. So it's okay for it to kind of pick randomly amongst them, but as the model gets better and better, it should start committing to a specific code, right? Rather than just randomly picking between them, in which case we want our temperature to be lower, so we can essentially just go ahead and update our model, right? Update our temperature parameter. So to do that, I actually missed one method inside our model, and this will be the temperature. I believe it'll be in the Wav2Vec2 for pre-training. Let's see here. We have our, right here. Yes. So right here, let's just write a quick helper function. Def set Gumbel temperature, self temperature. And this is going to do self.quantizer.temperature is equal to temperature. So it's just a quick helper function to take the temperature, and we can change it manually right here. So we can then go ahead and update it ourselves. So for our temperature, let's go ahead and go to our training function. To do this, it's pretty straightforward. Our Gumbel temperature is going to be max, because we set a minimum threshold. So if we look at our pre-train, we can see that we want a min Gumbel temperature of 0.5. It starts from 2, decays to 0.5, and it decays at this rate. And this is basically the parameters that the model itself uses. So we're going to do the same thing. So it'll be max. It'll be args.max Gumbel temperature times args.gumbel-temperature decay to the power completed steps. Right, so basically multiply this by our decay to the power of however many steps we completed, but you only want to do this as long as it's greater than args.min Gumbel temperature, right? We want to make sure whatever the min is, if this whole operation is less than 0.5, then we're going to go with 0.5. That's why we have max here. That's our Gumbel temperature. So we can now do if has adder model module, which it will in DDP mode. We can do model.module.set Gumbel temperature, else, right? Otherwise, let's go ahead and X out of this. Else, we will be doing just model.set Gumbel temperature. Again, Gumbel temperature, just like that. And now that we've done that, we can go ahead and do logging. Logging is not that interesting, so maybe I should just, I guess I can just copy the rest of this. There isn't much more in terms of, yeah, there isn't much more to really care about after this. It's just a repetition with some extra logging stuff. So let's just go ahead and toss it in there, and we'll walk through it instead of me typing. So basically, after we set this Gumbel temperature, oh, copied it twice. It's time to log our results. We're going to go ahead and grab our losses, contrastive loss, diversity loss, perplexity, hours per batch, percent mass. Just go ahead and grab all that information, right? And then if we have multiple GPUs, we need to actually gather them and average them up. That's basically what I'm doing here. The reason we're gathering them is, well, because they're on multiple GPUs, so we need to copy them over, and then we'll add them together and divide by the num losses. So that's important for these because we only want to compute this stuff per loss. So we want to make sure we reflect that in our final operation, and then hours per batch and percent masked is fine. We can just grab those as well. If we're not in multiple GPU, then that's easy enough. We just scale it and we're done. We then go ahead and create a dictionary with our log. We're also going to store in here our learning rate, our current temperature, and the grad norm, so we can plot that. We can print all that stuff out right here, pretty easy. And then we can write that to the progress bar, and then we can write that to weights and biases if we're doing that. During evaluation, nothing really changes. Our forward pass looks identical. We just throw the model to evaluation mode. Now that the model's in evaluation mode, it is important to see that here, that this is why we actually wrote in the Gumbel-Softmax method. This is why we wrote the, let's see here. Here we go, if self.training. So in the evaluation mode, we're going to select the most likely code vector. In the training mode, we're going to sample from our set of code vectors using differentiable Gumbel-Softmax, right? So that's a key difference. And that's why we wrote both of these. That's where model.eval most matters. And so yeah, we're just going to loop through all of our data, add together all our losses, all the different losses and everything from the multiple GPUs, gather them in, store them, divide them up by the num losses, and then go ahead and print that to console2, and throw the model back into training mode. And then we can go ahead and checkpoint, like every couple iterations, go ahead and checkpoint everything. Once checkpointing is done, once we've completed everything, then go ahead and iterate our number of completed steps, update our progress bar, and then go ahead and reset all of our accumulate steps and all that to 0. So it'll be ready for a new accumulation. So will this just work, or is there bugs? Let's find out. Okay, looks like we immediately have a bug. Can't open because I think I just called it train. Let's give it a try now. Okay, we're getting close, but it looks like we have an issue. Key error, masked time indices. So let's see what I called it in the utils. So we have here in our batch, that'll be in the dataset, we called it just mask time indices. So let's go ahead and fix that in our train. So it should be just mask time indices. Okay, good. Looks like that worked. So let's go ahead and try running it again. All right, moment of truth. Nope, not yet. We have a none type, outputs diversity loss, has no attribute detach. Oh, interesting. We don't have a diversity loss. let's check here first. We're going to check in our model. Actually, yeah, there's actually two things we need to still do that we haven't done yet. We'll add that in just a second. Let's just print the out right here in our model. See what it gives when we pass our data through here. But it looks like this diversity loss oh wait, I spelled diversity loss wrong somewhere. Diversity loss. There we go. Which means you are being unused. Okay, that should have fixed it. Okay, yeah, we can see it's none here because I actually just misspelled it. Before we actually train this, there is one important thing that I totally forgot to do. We'll add that in just a second. We need a better weight initialization, but let's make sure the forward pass actually works first. Okay, good. We're making progress here. Unsupported operation. Some elements of the input tensor written to a single memory location. So this is code vector probs. Okay, let's check it. Code vector. Okay, let's see here. So it's breaking on this line. So the reason for that is, let's see, we're just indexing from 0 to batch. Code vector. Oh, yes, of course. This shouldn't be code vector probs. This should be code vectors index, right? Index. So this shouldn't be probs. This should be index. There we go. Code vectors index. There we go. Of course, right? We don't need the why are we copying probs into probs? That doesn't make any sense. All right, let's give it another try. Always a new bug that we get to find. Hopefully this time we'll have more luck. All right, looks like it is inferencing, and so we'll let the eval loop wrap up. Now this is gonna maybe we should test after we do this. I'm just gonna copy paste this in again. We need to, again, remember, we have like a float tensor. We initialized, this one's fine, but we initialized our codebook here, but these are actually all just initialized as zeros, which is not helpful to us. We need to make sure we initialize everything correctly. So let's go ahead and add that in as well. This is the standard weight initialization strategy. We're just going to we're just going to go ahead and initialize everything kind of how they did online. There's not much logic to this. The main thing is in our Gumbel-Softmax, we're initializing our code vectors with a uniform distribution. So there you go. Everything else is kind of just a standard initialization, nothing fancy. If we add this in, we also need to make sure we add it to our actual script. So let's go ahead and do that. We need to make sure we add to our Wav2Vec2 model right here. Oh, so much code. Here we go. Wav2Vec2 for pre-training. We're going to do self.apply, and we're going to do weight init strategy. So that's going to go ahead and actually apply it. There we go. And we give it the config because it looks like for some of these things it needs it, right? The initializer range, which I specify again in my setup. So let's go ahead and give this another try. Yeah, so it's always, bug after bug. So we'll let this happen. It looks like the forward pass worked out. You can see that we have a batch hour, so we're doing almost about half an hour worth of audio, which is kind of cool. So we can look at GPU utilization. Yeah, so we can see we're only using about half the GPU memory here, so it's not crazy. Okay, sorry, this also might slow down the recording a little bit because OBS Studio and training a model typically don't go together all that well. But let's just see if it works for a couple of iterations, and then we'll call it there because who wants to watch a training loop anyway? All right, let's see. There we go. All right, so yeah, we can see things are training. We can see we're masking out almost about half of the data every single time. About half every sample is being masked out. So about 50%. And we're doing about almost half an hour worth of audio in every batch. In the original paper, they're doing about 1.6 hours, but that wouldn't be very hard to do if you just had like 8 GPUs without too much of an issue. And yeah, that's fine. The learning rate's 0 because it's going to be, it's doing a warm up, right, for a bunch of steps. And we have our grad norms here. So we can see that it hasn't exploded yet, but this will kind of end up stabilizing out once it's kind of trained for a bit. So I'm not obviously going to make you watch a training loop. It'll be much more interesting just to look at the final results. Let me pull that up real quick. So we're going to be looking at the reports, Wav2Vec2 base. So I trained a Wav2Vec2 base model, and this is kind of what the results ended up looking like. We have so this is the overall loss, kind of just decreased over time. There's very little evidence of overfitting, and this model actually doesn't even look like it's converged yet, so there's still more opportunity to train it, but I didn't want to wait more than 100. I think it took about 3 days to do 100K steps on a 4x A100 node. We can see perplexity here. Codebook perplexity is indeed increasing, which is good to see. So increasing codebook perplexity means there is a larger increase in codebook utilization. And in the same way, we have our diversity loss, which is inversely related, right? So minimizing the diversity loss is equivalent to just increasing the codebook perplexity. You can see initially it kind of jumped up in your perplexity, right? Like, oh, let's just use everything because it doesn't really know. But then slowly but surely, as you train your model, the perplexity will start to decrease because it starts to do the index collapsing, and it just kind of settles on a couple of codes and says this is good enough. This is why the diversity loss is so important, because the diversity loss is what penalizes that. And once it gets bad enough, it affects the model enough to start actually utilizing the codebook, and you can start to see it decrease again, which is kind of cool to see, right? So this is kind of your standard model. Yeah, so this is just 3 different runs concatenated together. Okay, good. So that is our Wav2Vec2 implementation for pre-training, right? Nothing fancy. It just takes a long time to train. Training these models typically are pretty, it's a little bit unstable. It maybe takes a couple of tries to get it right, but it's kind of seems to work out. You can debug it pretty easily from just looking at your different loss curves to see how things are going. And also, of course, taking a look at the gradient norm and things like that. So now that we've done this, we have written a Wav2Vec for CTC, right? We do have this model here. Now training this is not all that complicated. I actually ended up using they have an example on the, let's see, they have an example in Hugging Face for training a CTC model. So you can see that here. I basically followed this exactly because the Hugging Face trainer is quite nice where you can load any model you want into it. Any PyTorch model will work in it. So I just went ahead and followed this almost identically to train our model on that. So how that worked out is essentially this. So we can actually look at the code because there's no reason to type any of this. This is our Finetune Wav2Vec2. Basically all we're doing is just loading our model, nothing fancy. And what we're doing now is we're loading our Wav2Vec2 with CTC, with the CTC tokenizer, because we're going to need that. We have our Wav2Vec2 collate function for CTC. This function right here, we did not write because I basically copy-pasted it from that tutorial. So if we look at the data loader right here, model, where'd it go? Dataset. They had this method right here to do Wav2Vec collate function of CTC. It was taken directly from the fine-tuning example, right? So it came exactly from that link, and there's nothing fancy about it. All it is basically they have, just like my collate function, they have a collate function with a call in it, and what it does is it grabs the input values for the audio, grabs the input IDs for the labels. These IDs have already been tokenized. It goes ahead and pads the audio to the max length, or to the longest thing. And then it pads the targets, the indexes to that. We then also have a attention mask that we can just produce here pretty quickly, filling with negative 100 into labels, so we ignore the correct things. So we don't really need this anymore. And then we have, we can store that batch label here, and there we go. We now have a simple collate function directly taken from there. You can get more information there. I didn't want to go through this too much. We wanted to mostly focus on the pre-training. So now that we have that, we can then go ahead and do the fine-tune of the Wav2Vec, and I didn't even bother writing a training script. All of this was just taken directly from them, and we're using the standard training arguments, we're loading in our data sets, and we're using the standard trainer, right? Standard trainer. And this trainer only works if you do one thing. So one key thing to always keep in mind. If you want to use your model in Hugging Face, it expects a couple things. The main thing is that it expects a config file, or a config file that works in this way. So if you look at our utils.py, we have our Wav2Vec2 config here, standard data class, nothing fancy. But at the very end, you just want to throw this in here so it becomes compatible with the Hugging Face trainer, because the Hugging Face trainer tries to convert this config to a dictionary. And if you don't have this method here, then it breaks, right? So you just want to make sure you throw that in there. But now that we have that, you can end up just fine-tuning a CTC model on our pre-trained weights. And so the question is, how good is this model? So let's go ahead and just look at the results, because that's the most interesting part. If you need some, I should have started with this actually, but if you need the LibriSpeech dataset, you can go ahead and just like utilize these chunks of code here that'll automatically download and prepare it for you. But here's the key idea. Using Facebook's weights, we get a 6.5% word error rate, which is our standard metric again for speech systems, right? For speech recognizers. So we have a 6.5% word error rate. And so I trained 3 models. I took the weights from the original Hugging Face implementation. I tried my own weights, the ones that I pre-trained for 100K steps, which were clearly under-trained, but that's fine. And then I started with a completely randomly initialized model. And the cool thing here is that we actually learned something meaningful. Notice that when you start with completely randomly initialized models, so this is a random convolutions, a random transformer, everything is random, completely from scratch, we get a 69.5% word error rate, which is unusable. Anything under 20% begins to be pretty usable, and then anything under like 7% is basically perfect. So we can see that the Facebook weights, of course, trained longer and better on more resources. It does much better. So it's kind of hard to match it with just a couple of GPUs that I have lying around, but we do have a 15.5% word error rate, which is not bad, a very usable ASR system, right? So we can kind of go ahead and use that, and it's totally fine. And there isn't really much more that I wanted to cover. Again, let's just cover the main high-level ideas. Wav2Vec2 is a end-to-end model to both quantize and pre-train on raw audio. It leverages the Gumbel-Softmax technique for the quantization just to maintain more stable and differentiable, basically, quantization operations. And the main novelty is we did span masking on our inputs to the transformer, and we minimized the cosine similarity between a output embedding from a transformer and its corresponding quantized. And this means we had to sample a bunch of negatives to basically act as like the distractors. But now that all that kind of comes together, we're able to train a full end-to-end model, whereas before Wav2Vec2, you typically have to do these in 2 stages. You'd have first a model that you would train as a quantizer, then you'd use that model as an input to another transform model after the fact. So it's kind of cool that we get to do both of them end-to-end right here. But that's basically it. This was a pretty long video, as this is a relatively challenging implementation, but we have lots more fun implementations to come. This is probably one of the most popular ASR models that exist today, other than maybe Whisper. So I'm going to call it here, and I will see you all in the next one.